Welcome to Open Discussion, Flat Earth and More. I'm your host, Jose Gonzalez. Oh, hell no!
Ladies and gentlemen, we are live! Welcome everybody for joining us in this special edition of not Open Discussion Flatter or More, but let's try and find the curve. I am currently joined by Toady Liley and George Natiuk. Jesss Koslowski is confused on the side chat, say now! Yeah, it was a misunderstanding, a miscommunication about times. So Jesss Koslowski, I think George is gonna send you the link. You can join whenever you want. Let me introduce you guys. You can take over from now on. I will mute myself and I will kill my camera. Carry on. I will be very attentive. If you need to share the screen, I will do so.
Fantastic. If you can hear me at the moment, I'm going to share my screen, Jose, and then you can let me know if it's come through.
Yes, you're up.
Fantastic. And everyone can see it. Shall I start? All right. Fantastic. I'll kick off. Hi. So everyone knows me as Toady Liley. I've been on the panel a couple of times, and this presentation came about really from a really good conversation on a closed hangout, actually, after a show with Ali B and Mind of God. And of course, we were still talking about the various tests that can be done. And I went away to sort of rump us up, I suppose, some material that could be presented, especially around sort of theodolites, surveying, straight lines, and that kind of information. Now in searching, that kind of information out, I came across some really interesting things. So what I've got is a nice little presentation today, and I'll take you through what's in the presentation in a sec. Obviously, this screen here is a little bit of a joke. I'll let people work out what Toady Liley really means. You've seen me with two avatars. One is the sun sign for Leo, and the other, of course, is the all-seeing eye of Horus. Take from that what you will, and I'm sure Pete will have some interesting theories as we start. Hopefully, I'll be joined by Jessie, but George is here at the moment anyway, because one section of this presentation, it's a very visual set of presentation. I've left the maths that there is and the angles till the end. And not a lot of them are actually needed for the particular observation that we'll be looking at today, or the experiment that we're looking at. And it'll be great to hear firsthand from Jessie, about that, and then obviously potentially asking questions when maybe we open up at the end of the presentation. So without further ado, I will kick off. So what are we going to look at today? We're going to look at surveying, sort of what is it, and why would you do it? Surveying, how do you do it? Because I think it would be really good. I've had a little bit of experience myself, obviously not as much as Jessie or George, but I think a lot of people maybe don't understand some of the techniques there. I've heard lots of things about lasers at 3 miles and don't know what a theodolite is and information like that. So I think it'd be really good just to help educate everyone a little bit about really what surveying is and some of the techniques there and some of the equipment. Then we'll look at curves and large constructions, where I've got quite a lot of experience on that, and you'll see some of that. We hear a lot on the internet about CERN and conspiracies and the Mandela effect. And I'm someone who's been into CERN. I've been 100 meters underground. I've worked in those tunnels, and I've seen the people who work there. So, again, on the open panel, people can ask me some questions, and I've got some good pictures to share with you, that I took myself, right? So, not stock photos. These are photos that I took in Ferney-Voltaire, 100 meters down in those tunnels about 10 years ago now. And then a little bit of background on me, just to sort of a little bit about my credentials and what my interests are. And then into Jess's lake experiment, which is absolutely fantastic. It's a great experiment because it It abstracts a lot of the normal things which we get thrown at from the flat Earth side. We say, oh, you're assuming R, you're assuming this, that, and the other. This lake experiment is fantastic because it really assumes virtually nothing. Yeah, everything is built up from the ground up. It assumes two things, and we'll get into what those two things are later on. There's a photo walkthrough then, and Jessie hopefully will be online to talk through that. Then we very briefly touched on GPS. It's not really used in the lake experiment. I've sort of separated that out, but of course, in terms of mind of God and wanting to validate GPS against straight lines, I thought it was relevant, so I put a little bit in. And then finally the results, which is where we get into the maths. But this is a very, very visual presentation.
If you mind, yeah, I was about to introduce you, George, to get a minute to.
No, I'm getting out of here. I just spoke with Jesse. He and I were both under the understanding that this was going to be at 11 Eastern time. Jesse can't make it until 11. He's not by a computer. There's big mix up here, and he would like to have this shut down until 11. He said it's too important to miss, but he can't show up until 11. So it's up to you.
Yeah, I choose to continue the show. I will not shut it down.
Okay.
It's up now.
Right.
I apologize.
We'll get you later. Bye.
Yeah, and if you can join at 11, George, that'd be great. Okay, I'll keep going, Jose, yeah, because it could take an hour to get to the
yeah, carry on, yeah. The show is up,
okay.
and the show won't stop.
Yeah, okay, good. Right, surveying why? Why do we do surveying? And by the way, if there's lots of questions at the end, hopefully when Jesse and George join us, if we get out of my knowledge set, we can look at that. But I can, a bit like Rumpus, talk for hours, so we'll keep going. Okay, surveying why. Triangulation points, we're going to look at those, measures, maps, tools, the basics, and why we measure our physical environment. And why do we look at buildings and why do we look at the landscape? So what does surveying achieve for us? Does it prove anything really? So we all know about this 8-inch per mile drop, or roughly 8-inch per mile. We can debate what that is. This formula is often, I think, poorly used by flat earth enthusiasts and applying wrongly around the line of sight. So as the diagram shows below, what this is a level. I think it's a dumpy level actually shown in the description. And what it's showing us is that the dumpy level can measure a horizontal line and is there measuring a horizontal line. And that horizontal line, which is of course perpendicular to the center of the earth, i.e. gravity, which is the drop that we look at below, a plumb bob. So whether we believe in gravity or not, we do know that a plumb bob will go level and point to the ground. So this is a horizontal line that is projected level to that plumb bob, and that's slightly different to the line of sight, especially over a distance. Now, over the years, obviously many thousands of surveyors have measured, recorded, and adjusted and allowed for these kind of errors, over probably hundreds of years now, and regularly measuring the Earth day in, day out, and adjusting for this curvature. I have touched on there this little star. I will share afterwards the whole presentation pack. By the way, I'll put it somewhere where everyone can get access to it. I don't want to debate what down means at the moment. Down is a big question. I've put a link there to what down really means. I don't think it's particularly relevant for the material that we're going to go through today, because down in terms of the material today is a plumb bob will point down if we drop a plumb bob from a string. But we can talk about the center of mass or the actual center, the real gravitational center or the geodesic center and so forth. They're a little bit of a red herring really for what we're looking at here. So what we're assuming here is that we've got a level, we've got a plumb bob, we know which way is down, at least we're confident in that, and then we can take a horizontal measurement from that, and that's very different to the line of sight. So most countries have got surveying points and they're distributed through the landscape. These ones here are ones from the UK. The Ordnance Survey, I think about 150 years ago, started putting these in the ground. In the UK, they tend to be one of these things where you can actually sight from a high point because you might well use a theodolite or similar instrument from one of these. As you can see, the one on the left there, you've got lots of fixings that you can use. And these are very, very accurate points. The other interesting thing is if you look on the right-hand side, that funny little symbol that looks like probably like a little theodolite that measures something is actually the ordnance sign, and that's linked to the army. So I think it's supposed to be a tripod with a little, a little theodolite or a level, a dumpy level on it. But it's also known very much as the sort of military or army symbol. If anyone's got any army surplus things, clothing or whatever, it'll often have that symbol on it. If you look at Jesse's site, and I've got the links within this presentation, you can go there and you can have a look at a lot more information on this. It's quite an interesting thing. Wrong way. Now let's move to the US. I wanted to do UK and US, of course. They have, again, in most countries in the developed world, this global conspiracy probably goes quite deep, if it is such, because all around the world, they put these little plaques in the ground. You've seen the ones in the UK now, and we're looking at the ones that are from the US here. In the US, they're called USGS, which stands for the US Coast and Geodesic Survey Points. Just like the UK, they have this global symbol of the triangle and the dot on them, as you can see on 3 of them there. There's an arrow on the other one. Don't know what the arrow means. And obviously, some people have linked this in, with the all-seeing eye, the dollar bill, and the Illuminati. I think it's probably just a symbol, to tell you the truth, that they use on maps, and then they relate to the real world. The examples here you can see are quite interesting. They've got dates on them. They've got quite a lot of information that's stamped on them. And then these bronze plaques are actually set in stone. So they're incredibly accurate in terms of their height, their latitude, and their longitude. So people will actually go out there with a blowtorch. They will check, the position of that central dot that's in it. You can see in that middle one there that the lead, which they've used to set it in the stone, is actually sort of leaking out from the side when they reset it. And you can actually see, if you look in the middle picture, that it says it was reset in April 2002. So obviously someone went out there, they cleaned the dirt off this little bronze plaque, and then they heated it up, and then they reset it. Now, some people go around and actually, look for these plaques, because they are, I think, every few kilometers within the landscape, and try and get pictures of them and so forth. And you can go online and you can see thousands of these, which people have collected them, trying to sort of go around and get them all, a little bit like Pokemon or something. Okay, so I'll move on a bit. All this is context for the fact that surveying goes very, very deep, goes very deep into our landscape, and goes very, very deep into our culture, and we'll get to maps in a sec. So 101 of surveying, what kind of things are used? I think on the channel you've heard Jessie and others talk about various things. We'll go through them quite quickly, just to set a bit of context. And I'm sure, once Jessie joins later on, people can ask some specific questions about them. But I've used some of these tools before, throughout the last 20 odd years, so I can talk, reasonably confidently about quite a few of them. A total station, which is a fantastic tool that sort of brings the world of digital and GPS together with a theodolite. You've got all your materials there, and I think I'll let Jessie touch on those later. A dumpy level, which is what it says. It's sort of short and squat, and we saw it earlier. It's very, very good at giving you levels, and is used very extensively, especially in the building trade, in my experience. We'll go on to the inclinometer, which of course you can get an incline from. A plumb bob, which is just a weight on a piece of string. I'm sure if you've done decorating in the house, you've used those as well. Next up is, of course, a tripod, which you put some of these things on top of. We've got a plane table, and I've got a really nice picture of a plane table being used about 200 years ago or 150 years ago coming up, which is a great picture, which I put in for Ali B, and we'll see why in a sec. Then you've got another picture of a total station. You've got surveying tape, which you can use to measure quite long distances, 100 meters or so, I think, the tape that I've got. You might get different distances, but you're probably not measuring over that with it. Then you get into rods.
We can see your mouse. If you want to move your mouse over and hover it, we can see where you're.
All right, you can see it?
Yes.
Fantastic. Okay. Thanks, Jose. Surveying rods. Now, in the UK, you'll often hear these things, rods and chains, right? It's kind of like a traditional UK thing. When you're buying a house or something, you hear about rods and chains. It's something the solicitor always brings up. So this is what they are. The rods, of course, are measuring rods, and they can go quite tall, and they've got, little delineations on them. And you'll see later on Jessie using some of those in the observations that he did at the lake. And then, of course, chains. Chains, I think, are used for measuring out sort of normally fields and things, in my experience with farmers. I'm sure they're used for other things as well. And they're just a handy way of having a set measure where you can mark out a property or the line of a property, right, when you're buying a house or a field or something like that. Then we've got the surveying traverse. We've got the world of GPS coming in here. This is we'll see one of these later, and we'll see Jessie using one of these later on. Really interesting. Then we've got a prism pole. This is sometimes used for line of sight with reflection, so that there's I think also a staff, surveyor staff that you can get as well, which will make sure that you're online. And then, of course, a map where surveying is done. So again, a lot of this is just for context. As we go a little bit deeper into using some of these things, it's really good for people to be familiar with the tools and how we lay out straight lines when we go into the field. Okay, the 101 of surveying. What is it, and where did it come from? A couple of these pictures I put in specifically for Ali B, because we had a joke the other day about machetes, and in this open hangout, he had this idea of sort of going and doing the Great Land Surveys, which they did maybe 120 years ago in the UK. you know, people with hats and machetes, and they cut through the wilderness. And as these people here, you can see some on the left in a very hot country, possibly Egypt, I don't know. Some on the right looks a little bit more like, I don't know, Yorkshire in the UK or something like that. And of course, the guy's got his pipe and he's got his little level there, and he's got the guy that goes and holds the staff. Surveying's always a two-man job normally. It's quite hard just to do it on your own. It is possible, but quite difficult. You often need someone to hold the pole and someone to look through, obviously, the theodolite. And then you've got a very beautiful theodolite there in the middle. We'll get into theodolites a bit in a sec. But, you know, wonderful instrument, probably sold in auction for, you know, a couple of £1,000 or something. Yeah, historic theodolite. The great thing about theodolites is they've not really changed very much through the years. And that's a really important point I want to make here, that this simple equipment has been used to create all of our maps, really. It's been, you know, building all of our great tunnels. I mean, few notable exceptions in recent years, and I'll touch on them a little bit later, actually. But, you know, the great tunnels, certainly in the UK and probably in the US as well. Of course, the canals, viaducts, railways, bridges, and other buildings since the Industrial Revolution. And of course, the Romans, Egyptians, and Greeks had their own, you know, simple tools. I'm sure they had lines and weights and sighting sticks. Pretty sure of that. They may even have graduations on things. You know, if we look at the Antiochera mechanism, which they found when they dove on that boat, you know, they had brass and bronze, and they could mark it quite accurately with graduations. So they may well have had other tools that maybe we've not come across. And really, not a lot has changed, I think, in the last certainly 100 years when we're building accurate structures. Of course, they will have come across the errors that they see, and we'll look at that before. And I think maybe that helps people reflect that we live on a globe, because when you're surveying things accurately and you keep getting these errors, you know, you need to start explaining those. And then the final point here really is that all of this predates drones, GPS, satellites, computers, the whole digital age, right? All of this amazing building, really big buildings, you know, straight lines, bridges, railway lines, cuttings, tunnels that join up through two sides of a hill, all of that was very possible, and that level of precision, they could do it with just simple tools being used. Next up really is about our maps. So you've got two views of a map here. Just happens to be somewhere reasonably close to where I live, actually. So, you know, you've got a map, you've got a satellite image on the left, and then you've got an actual map on the right. Now, I guess everyone on this knows that I'm really quite familiar with maps. It's something I've worked in for a very long time, actually. The map on the right is one that has been surveyed over probably about 300 or 400 years, actually, in this particular area. So people have built up and measured, and they've done property lines, and they've built it up, and they've pieced the map together. This map didn't just come into existence, I don't know, whatever, 10 years ago when Google suddenly decided to, you know, to set up and start taking satellite images. And the really interesting things about most maps, not all maps, but most maps is, especially of areas that have been populated by humans for a long time, is the satellite doesn't really help. There is a great deal of difficulty actually in trying to get satellite images to fit the base map images. And you'll still see that if you switch on your, you know, sat nav or something, you know, and often you'll find that the road is in a slightly different position to where the road actually is, you know, in terms of a satellite image. And all of that is to do with the way that the maps have been built up, from tiny little pictures and people surveying bits of the landscape over hundreds of years. They've built a patchwork of all these little measurements that all interlink together. And of course, once satellite images came along and we were able to have these wonderful satellite images, then we had to make adjustments and started to change the maps a little bit. So Google Earth obviously does these overlays. They're called an overlay. It's because that's back to the day when you used to put a sheet of tracing paper and you used to trace through it on a map. That's why they're called overlays in the industry. And line draw maps obviously are the basic reference set. Now there's a lot of mapping coordinate systems, and we've touched on some of the panels on that before. I'm just mentioning three here: ENU, that's Ealings, Northlings, and up. UTM, WGC84, and there's a number of others, yeah. Plus there's local systems. I think the US is state plane. It's not one I'm familiar with. I've not worked much in the US. Or of course, Ordnance Survey in the UK, and I'm very, very familiar with that. Anyone who lives in the UK will be familiar with the Ordnance Survey maps. And they're, you know, very, very interesting. And we do them at school in geography, and you know, we look at those maps and we understand them. And of course, then there's many maps that are used by sailors, the military, and civil society, and all of this long before we had satellites and GPS. So just to make the point, we were accurately mapping the landscape, and we were finding our way around long before satellite and GPS came in the last 30 years. Here we see this satellite view, and as I say, I touched on the point I think before that maps are very rarely derived from satellite images. Few exceptions, maybe very remote areas, maybe in Africa or Asia, you know, where you really can't get in very easily. Your satellite image is very good, very useful. But then there's not a lot of roads there either. Whereas most of the other areas, it's been done traditionally. Okay, surveying then and now. So here's a theodolite, which is obviously a tool that will take a perpendicular level, and it also allows you to finally calibrate vertical and horizontal measurements. So you can actually change, where up and down is, and you can calibrate to an azimuth of some sort on 90 degrees to level. And then you can use an optical zoom, and that guy there in the hat, again, a great gentleman with his riding boots on and his sort of leather jacket, is out in the field. He's looking through that optical zoom. And that optical zoom has got crosshairs, and we'll see that later on Jess's theodolite or level that he was using. I think reflecting these pictures as I pick them up from Google.
Apologize, sorry to interrupt you really quick. Do you have a YouTube channel? Because I didn't add you in the description box, and I feel bad, but I was looking for your channel and I
don't have a channel.
No. Thank you. Carry on.
I don't. Times have changed, but it seems surveyors may have changed shape a lot. Their equipment has probably stayed pretty similar, as you can see. And you'll see that later from Jess's pictures. So again, I think making the point, this is quite low tech. Later on, we will cover whether lasers are used on total stations or theodolites. Once Jesse joins, if I keep talking long enough, because I think it is a good point to talk on. This one certainly has got no laser that the woman is using there, but it has got crosshairs and it has got an optical zoom on it, a very strong optical zoom. Okie doke. Surveying, how? So some basic details around surveying, how we measure in real world situations, plus looking at the theory of curvature and sort of introducing that concept. Okay, so how does the theodolite operate? Basically, you've got a level platter and it's perpendicular to the ground. You can see here the plumb daub and it's over the base point. As you can see, the plumb is hanging down there. You've got a zenith, which is obviously upright. And then you've got horizontal line. And of course, the horizontal line, as we touched on earlier, is very different to the line of sight. And that will become increasingly important as we go through the rest of this material. You've then got a scope that is set on the top with crosshairs, and that allows you to zoom and accurately measure at a distance off the staff. Now, there's also a bubble level. It takes quite a while if you've ever used a theodolite to get the bubble level accurately set, because it's a 3D bubble level, of course. And you've got those three little level gimbals that you adjust at the bottom, that you rotate up and down, which are on the device to make sure that you get it exactly level. So it really takes quite a lot of time to adjust it, and then you can start taking your measurements. Now you can either measure angles of elevation or depression, or you can measure horizontals. And it's an important point, as we'll see later, on why you would want to look through something and have a horizontal line. The key is obviously on anything that is flat. If you've got a plumb bob and that plumb bob is pointing down perpendicular, if you look through that scope and you've leveled your little your bubble level, you will have a perfectly horizontal line, which is of course horizontal to the direction of down, which we take as pretty consistent because it always measures down somewhere on the earth. We'll get into where the curve comes in a little bit later. So at a local level, at a very short level, where you're going over short distances, you can see where down is. Here's just a diagram just to explain a little bit more about the theodolite. I mean, it looks complicated, but it's not really. Again, you've got a sight axis, you've got an eyepiece, you're looking through it. You can see in different directions. And then you've got a bottom horizontal circle where you can measure 360 degrees in all different directions. And then you've got a top where you can measure angles up and down, or of course you can measure the horizontal, which is what we're mainly interested in, I think, today and going through this material. And of course, that eyepiece has got a crosshair on it, so you can accurately look at the target on a ruler or a staff, which we saw earlier. Okay, this looks a bit complicated, but really I'll try and break it down to make it a little bit more simple. In this particular example, okay, not in the one that we're going to look at later, but in this particular example, they've got a dumpy level, and a dumpy level will measure, horizontal once you've got your adjustments made properly. You've got a base, and you've got a rod that you're sighting through. So this is a very typical thing you do in the field, surveying, looking at a staff, taking a measurement and seeing what that height is. And then, of course, here you've got two heights. Now, in this particular example, the staffs are being used to measure downwards. So you're measuring from the horizontal to the ground that's below. So in this example, you're not measuring from the ground up. You're measuring from that horizontal 360-degree line of sight. You're measuring forward and backwards from two staffs downwards to whatever the landscape happens to be. Now, of course, you've got to measure from something. And what are you measuring from here? And I'll use my mouse pointer, actually, Jose. It's a really good idea. You can see here that this is the base location. So this, for all the surveying that this dumpy level is going to be doing in this session, is being measured from this point here. Now, of course, the construction of the dumpy, they know, theodolite dumpy, same difference really. You know that you're 1.4 meters from the ground. So you're measuring from this horizontal line of sight against this base point, which you know is 1.4 meters down. So then you know this is completely horizontal. So wherever you intersect in the staff, when you look for your crosshairs at this direction, or you turn it the other way, which of course what you do with a level, you take a number of readings in different directions, you start to work out this is 1 meter down, and of course this is 6 meters down. So you know what this point is, and you know what this point is, all relevant to this start point here, the origin, which will later on become really quite important. Now in this particular example, they're using a very accurate GPS unit to get this particular elevation. So their start point is being validated against GPS. Okay, we are not going to be doing that in the experiment that we see. We're going to use a different level point, and quite an interesting one. But in this particular example, typical field use, we've got the actual elevation here. It's quite high up, actually. It's 1637 meters. We then add on the 1.4 meters, and then we measure from this line, and we can measure downwards so we can get the the position of the landscape. Okay, I know that's quite a complicated picture. It's probably the most complicated one that we're going to see today. Okay, on to the next, theodolite in use. So here we see another example, and this is sort of the second example that I referred to. Now, in surveying, very typically you do something that's quite accurate, which is called backsighting and foresighting. You see, the beauty is that you try to get rid of a lot of your errors by sighting in two different directions. You sight in one direction, and then you sight in the other direction. And what you can start to do through that is you can start to remove errors where something maybe isn't quite level in one direction, or you've got a slight adjustment in another direction, because as long as you've always leveled out the theodolite or the dumpy level, whichever you're using, you can make sure that you're measuring in both directions and it remains consistent. And of course, that's what this is trying to show here, that you do forward to a graduated staff, back to a graduated staff, you then change your position to that known point, and then you measure from there. In this particular example, we've got not measuring down from the level, we're measuring up from a peg. And so here we see a technique where a position has been taken on the ground, a peg of a known length has been put in and measured, and then the measures are being taken against that peg. Often used, as you can see, sort of in building sites and in other circumstances where you want to measure up from something. So the previous one, we were measuring down. In this little example here in the excerpt, we're measuring from something. Okay, I'll go on to the next. Right, now we're getting to it. So surveying on a flat plane will always allow level backsighting at whatever angle you're at. And I think this is the key for the experiment that we'll see later. And I'll try and go through it because it's a really important picture that I created here to try to show everyone how this works. So what have you got in the top picture? What we've got is a hill or a contour of some sort. And we've got three positions that we're going to put our level in. And what we're going to do is we're going to sight forwards, and then we're going to sight backwards. And by sighting forwards and backwards, as long as we are perpendicular to the ground with our measurement, we can make sure that all of those levels will be completely horizontal to that 90-degree angle that we're measuring here. So you can sight forward, you can sight backwards. Doesn't matter what the contour here is. In this example, we're always sighting level, and we are level. Now that works really very well over a short distance where you don't start to get the problems of curvature coming in. Now let's look at the second situation below. By the way, this could be a flat earth scenario or a short distance. So this would definitely work if you're only going, I don't know, 10 meters. You have the curvature of the earth wouldn't come into it. You could sight level, it would stay level. The margin of error from the curve of the earth would be negligible. So 10 meters this way, 10 meters that way, it would work perfectly. Yeah, and this is often used for surveying on sites, right? Because the curve of the earth doesn't come into it. You're measuring only over a short distance. You're not worried about the curve of the earth. It's such a negligible amount. But when we go on to a larger scenario like this, we can start to see, well, what does down mean? So this first measure here, this is over a much longer distance now. We're maybe looking at, I don't know, 500 feet, something like that. So quite a significant distance. What you've got is you've got your first plumb bob, which points towards the center of the earth, which this one is, which is why it is 90 degrees. It's absolutely perpendicular to this piece of ground here that is going upwards, and it is pointing to the earth. But of course, you know, and that's the top of the curve, if you like. Obviously, you could rotate this picture to make that the top of the curve. In my example, this is the top, this is the side, this is the side. But hopefully everyone gets the idea that you are sighting, of course, and you are at 90 degrees, absolutely, and that is a horizontal line. But of course, that line, unlike this picture up here, does not come up level. It comes up short of this one up here. Because again, this one is adjusted perpendicular to the ground, and you can see exactly where the horizontal line goes across. And then the same here. So the idea of showing this picture is to link up to when we get onto the experiment later on, what happens when we're surveying over a distance where the curve of the Earth does start to play a factor, and we should be able to see that. So if you take those three levels out and you make them level to a set base. Now, of course, I've drawn a really nice hill here on a nice contour, and you could say, right, I'm flat against the hill. Of course, you have to get the heights correct, because otherwise, obviously, the height of this would come in lower. But we'll see how we get around that later on and how Jesse got around it in his experiment. But if you assume that you did take a consistent contour, you would be able to sight like this, and it would not be level, okay? And your line of sight obviously would be different. So if we go to the next. So onto the curve and some large constructions, and there's some really good photos I'm going to share here, of where I've done and been involved in some of the surveying, and then we'll move on later on onto the experiment. So accuracy in the curve. So the curve of the Earth is, significant really when you're doing scale construction for the reasons that I've just shown. Yeah, this is really due to the natural forces that act, i.e. gravity, and it's the tendency of steel or pipelines or other big structures to warp if you put them over a long distance where the Earth curve comes into effect. Yeah, naturally things will try and follow the curve of the Earth, believe it or not. And it's actually a very complex thing when you're doing surveying to make sure that you get a true straight line, as you've just seen from those illustrations that I've done, because it's really important that you do that if your construction so requires it. Now, the raw measurements are uncorrected for the deflection from the vertical, and they're referenced to the geoid. And the geoid obviously is, the theoretical projection that is around the Earth. These measurements reveal that the tilt exists between the vertical plumb directions at the end of the line. And that's what you've just seen in this previous picture, these deflections that exist against that line from the plumb, okay? And that's what I'm talking about. Now, over a distance, that becomes, significant. Where in New Jersey, I think it was, where Jesse did his observations that we're going to see in a little bit, that can amount to something like 1 arc minute in a mile of rounding off. And over that distance, obviously, you can get considerable warping. Now, why would we be worried about that? Why do we really care? Well, we care if we're doing the channel tunnel. The channel tunnel was built. It needs to be relatively straight, and it needed to meet up over, I think it was 20 odd miles across the channel tunnel between England and France, or Britain and France. And they needed to make sure it was measured correctly, and the big machines they had that dug it out, met correctly. So over a distance like that, it can become a problem. The next example I've got here is a VW car plant. It's a fully automated, fully roboticized, CNC machines, cutters, and robotic arms, and all that good stuff. And again, when you're running a lot of cars through a plant like that, something significant, warping or difference, if you're out by 20 centimeters, that's an awful lot when you've got machinery running on gantries and so forth. So car plants, another area where they really want to make sure that the curve of the Earth doesn't come in and create problems. And then we've got two more really good examples. So sometimes for some specific applications, you need to have a high precision of determination of the curvature and know what the tilt is. And obviously, probably the best example, I think, which Jesse touched on before, is the construction of LIGO, which is the Large Laser Interferometer Gravitational Wave Observatory. You can see it there. It's got two absolutely massive straight line sort of pipes where they're shooting beams down there, at different distances, and obviously measuring the difference in the time. They were trying to pick up, I think, gravitational waves between those two experiments. And I think they actually had two centers built in two different places. But again, you're building something over a number of miles. The curve of the Earth starts to come into that. Because they need to make sure that those tubes are absolutely, straight, literally straight. Yep. Not, just the horizontal, not a line of sight, actually straight, mathematically straight, let's say. They needed to take some very specific measurements before they built it. Another example here, we see, I'm talking about CERN, and I'll come on to CERN in a sec because I've got some really nice pictures to share of CERN that might interest people. And of course, Crossrail. Crossrail is a large railway. They dug a lot of it underground, as you can see here. Again, it needs to be absolutely straight. They need to have the machines that come in that put in the tubes that they make the tunnels out of, which are made out of concrete. And again, if you start to get measurements that go off, you start to have significant problems when you're digging tunnels like that.
Did I mishear you when you say you took some of these pictures? So this is not your pictures? Not
yet. Yeah, we're going to get onto my pictures in a sec.
Cool.
Yeah. I'm going to be really careful about what are mine and what are stock ones, Jose. Yeah. Because at the end on the panel, I'm sure people will ask questions about some of the pictures that I took, because there's some quite good ones coming up, hopefully.
Yeah, George jumped in the chat and he say himself and Jesse are going to be busy for another half an hour or so. So they'll jump in at the scheduled time that they thought it was. So they will jump in the hour mark. And yeah, I will keep it close for just the three of you guys. Carry on.
Okay, fantastic. That's good. I'll probably be half an hour by the time we get to that bit anyway. I can waffle on for quite a while. Just hang on a second, excuse me. All right, excuse me, I'm back. Got a cold at the moment. Right, so this isn't my picture. It's the only one I think of CERN that I show that isn't my picture. So what are you seeing here? CERN. It's a fantastic thing. This is the Atlas detector, and basically it's a massive, great camera. So all of this, if you just imagine it's just like a camera, this is the way that they explained it to me when I was at CERN working. Imagine this is just a camera. And what you're doing is right in the middle here, you're shooting down your little particles. And what you're doing is you're getting the particles to go so fast in two directions, around 27 kilometers. The particles hit in the middle. There's a huge explosion of particles. And what happens is all of this equipment is all of these, it's a bit like a CCD on your, on your SLR camera. Yep. It measures those impacts of those, protons, I think, that meet in the middle, and then all the strange and weird and wonderful particles that come up from it. And all of this equipment is surrounding just that one point when those particles collide. If you look at this picture, it looks pretty impressive. It's like an eye or something, right? It looks quite interesting. Look at the side, just briefly. You'll see this is 5 stories tall. So, a human, someone would be standing here about, if you can see my mouse pointer, about this high here. Yeah. And you'll see some of my pictures later on, which I took at the CMS. It's another big detector. It looks very much similar to this, actually. I worked around the CMS, and you'll see a lot of the pictures of me taking it through the bars, through these like green bars. Yeah. And there are thousands of scientists working here every single day. And this is all about 100 meters underground. Yeah. So it's all underground, very stable in the granite. It goes across between Geneva and actually France, CERN, and this is what it's all about. This is one, I think, of about 5 big experiments that they've actually got at CERN. And this is all about capturing that information. And when I look at that, it really does amaze me. They've got these things here are actually coolants, right? One of the very good friends of mine, still a good friend of mine, he still actually works at CERN. He works on these. These are CO2 coolants, and they're used to keep all of this electronics very, very, very cool, so you can make the really accurate measurements when the particles come out from this middle piece. It's just, it amazes me what humans can do and what our ingenuity can create. So here we are. Here is the Atlas detector, and you can see the corner of my hat there. This is one of the pictures that I took. This shows you the 27-kilometer ring around. This is the one that I worked on mainly, but I did go down into CMS, and you'll see some pictures from CMS in a sec. But this is Ferney-Voltaire. I spelled it wrong there. Ferney-Voltaire in France, which is where I worked. Atlas is the one that you've just seen, the Marin ring. And as you can see, they've got this big particles. They go around this 27 kilometers, and they get faster and faster. And then what they actually do is they pump them off to the side into this little ring here to get them super fast, to then collide them into this picture that you see here. So this is the Atlas detector. The Atlas detector is here. And as I say, they can't get the speed up by going around and round and round. So then they zoop them around here to get them super fast over this sort of booster, if you like, to get those really, really, really big explosions happening. A very funny thing, actually, while I was working there, there's actually 2 Jack Russells. Now, Jack Russells, I don't know if the American audience know what a Jack Russell is. It's a dog. It's a type of dog. It's a small dog, actually. And it's often used in Britain for sort of chasing rabbits, and it's like a rabbiting dog. And I think there's 2 Jack Russell Terriers that are working out there in France, which they bought from the UK, because when they first did the very first experiments, when they turned on Atlas and they started, Atlas, by the way, is the American-funded part of CERN. Yeah, it's got all the Americans working on it. And they turned it on and they started doing some experiments. They were like just testing it out, right? They weren't really looking for these new bosons or Higgs, whatever they were, particles, yeah, but they were like just turning it on. And it was at the period actually I was working at there where it did sort of, it was about a year in, right? And they were just doing some tests, and they kept finding these weird particle fluctuations, and they got very, very excited. They thought they might have found a new fundamental particle. And some of the physicists working there started to track it down, and it always seemed to happen at a certain time in the morning. And I think it was sort of, I don't know, 9, 10 o'clock, let's say, for sake of argument. Yep. They couldn't understand why this sort of measurement, they would start to see this new particle, and why the particle would always be, very timely. Yep. So they went and they experimented more and more, and they had a look, and they took some more readings, and they got into it, and they realized sort of which fluctuation in which bit of the complex it started to happen. So then they actually went and physically looked at the outside, because there's lots of access tunnels, by the way. If you drive around in this area, there's lots of access tunnels. You can see one here, and you can see another one here, and you can probably, there's another one up here, but that's one of them there, and that's another one there. And these access tunnels actually go in, down, so you can work on, as you'll see in a sec, what the tunnels look like, right? I've got some pictures of the tunnels, which are quite exciting as well. And so what they found actually was, and I'm sure people have worked it out in the chat already, that there was a family of rabbits was living about here. And those rabbits used to get up in the morning and then do a bit of burrowing and a bit of munching. And just the vibrations from those rabbits in that warren, caused enough of a change that it was picked up underground, 100 meters underground, by the Atlas experiment. So then they went to the UK, and they got some of these dogs to come out there, and then they got rid of all the rabbits that happened to be in that area. So that's why I mentioned the rabbits, watch out. Okay, so here's a real picture of the CMS. This is near CMS. This is one of the detector tunnels. You'll see what the tunnel looks like in a sec. This is another one of my not great pictures done. You can see up here, and I don't know how good it comes through on the screen, but up here is the magnetic field, and it's a really incredibly strong magnetic field. You have to wear a special badge if you want to go in into the tunnels to work. And you can see the huge ducting that's coming down from the roof as well. And of course, they've got lots of alarms here, because in the tunnels, they've got the big pipes, and in the pipes, they've got oxygen, which is why it says it's a oxygen hazard. It's a very explosive environment. This was from about 2012. When they were building the tunnels, people apparently used to roller skate around them when they didn't actually have all the equipment in them. So it's quite fun for people on roller skates. Apparently, all the people in CERN learned to roller skate so they could get round between the different experiments as they started to put all the big cables and worked in the tunnels. But obviously now the tunnels are full, and you'll see another picture in a sec of what that looks like, what the tunnels look like. But this is one of the entrance to the tunnels. And it's quite spooky when you're underground. There's no natural light, of course, because you're 100 meters underground. And you've got this massive complex. It's like a sort of underground city if you visit it. They got very good hot chocolates, of course, because it's French. Very good hot chocolates in the cafe there. So this is one of the tunnels, and as you can see, there'd easily be enough room for someone to roller skate down there if you didn't have that great big pipe in there. Here you see the big pipe. You see all the cables that they've got for pumping it in. CERN is only operational. This part of the collider is only operational for about 6 months of the year. And you can see again, while I was working on it, we were doing a lot of GPS. We were trying to make sure that the tunnel is straight, but it also needs to be at a known curve, because you saw earlier it goes in a ring. So yes, it needs to be absolutely straight. It needs to be absolutely level, which is really very important, especially because you have these very large magnets here. See these little sort of intersections here? These are special electromagnets, which are powered obviously from the cables that they have here. And these electromagnets, make sure that the beam is kept in a very consistent manner. And they actually power up. I can't remember when it is. I think they close it down during the winter, actually, to do maintenance. They only power it during the summer. And that's because I think in the summer they tend to have quite a lot of cheap electricity, because just the amount of electricity to actually power the collider is phenomenal. And so a lot of their projections and their budgets are all based on when the electricity is the cheapest. And then I think for 6 months of the year, they may have changed the program a little bit now, but when I was working there 6 months of the year, it was downtime and they weren't even using the, these tubes. But absolutely fascinating place to be. And these tunnels just go on and on like something from a James Bond movie. These are all my pictures, by the way. And here's another picture. This is a great one. This is looking in at...
and that is impressive, my friend, your own pictures on CERN. Carry on.
Yeah, they're great. And what you can see here is that's actually CMS behind. So we talked about CMS, and you'll see a picture of CMS in a sec. You can see that I'm actually looking through here, the green, you saw those like green, the sort of green bars and things that they've got, like down here, they've got these green bars to stop people falling off and stuff. This is amazing. This is a huge piece of iron and lead. And you can actually see how tiny the actual tube is. So this was really lucky. This was on a day I got to go up there. So one of the scientists said to me, pop up, go and have a look and take a photo, because it's a very rare site. So this is the injector tube, and this is where actually like all of the particle explosions happen. This is the shielding, because the particle explosions are so large that if a human being was near them, and you're not obviously allowed in this area when they're doing the actual experiments, it would kill you, right? The radiation would absolutely kill you, definitely would kill you. And you can see the detector in here, and we'll have a look in that sec. This is about 3 or 4 stories up here. And this is the tiny little particle tube that it all goes in, a tiny little glass tube. And it seems, you know, almost very, very fragile, right? Inside all of this huge stuff. And what happens is this big piece here, this green piece, sort of inserts into here, and then these two bits lock in the side of it, and then it locks into the actual accelerator itself. So it's a you know, fascinating you know, piece of equipment. We'll go to the next picture, which I think is a good one. Oh, yeah, there we go. So that's me about 10 years ago. Sorry, I've anonymized my face, but you know, I don't know who's on YouTube and watching this stuff. And some of this is you know, I think it's fine me showing these pictures. I don't think there's anything confidential in these pictures. But that's me with my hard hat on. Again, this was when I got to go up on that day that you saw the previous picture was taken, and I got to actually stand in front of the CMS detector. Now, that CMS detector is about, you know, 3 or 4 stories high. So you can get an idea that I was actually standing on a gantry. Someone was behind me taking the photo, and then we were looking actually into that detector. So if you see this piece here, all of this here, this isn't all opened up. It actually goes even further into here. So I was standing over here. This was withdrawn, which is why I went up there to get the photo. And I was standing over here, and and we're looking in that direction, actually into the detector. And this is the heart of the detector where you see that little, that tiny little tube go in. And of course, as I say, it's again, this is the CMS detector, which does a different set of experiments to the Atlas one. You know, still looking for fundamental particles, still exploding particles. And again,
how long ago did you take these pictures?
This was about 2012, I think, from memory. Yeah. So what, 7, 8 years ago? Yeah, something like that. Yeah. So yeah, and those experiments are still there. And this, by the way, they keep updating it, so they work all year round. And you can see these amazing tubes here. So as I say, one of a very good friend who I'm still, a Dutch guy, who I'm still in touch with from it, and he still works at CERN. You know, which is great because, you know, then I get to go down and still have a visit. If I'm in France, you know, he specializes in these pieces that you see here, which are actually CO2 coolant systems. He used to use CO2, and then they've moved to nitrous nitrogen or something, I think, liquid nitrogen, to start to cool it down. But it looks just incredible, right? If you think about all the things that people do just to measure those, you know, just like a camera is how they described it to me, just like a camera. Because I'm not an expert, by the way. My background is in maps and that kind of science, not in particle physics and the quantum realm. Okay, bit of background on me. So you probably guessed some of this already. Part of this presentation, I'm going to share some photographs about, you know, my work. You've seen some of that from CERN already. Pictures of my shop, or workshop as I would call it, because I'm from the UK. My interest in other things. I'm about 50, married. I've been working in mapping, GPS, IT, satellites, security, and that kind of thing for about 28 years. I've got a real passion, as you can tell already, for you know, what these pictures will show, and the idea of the sort of citizen science, which is obviously why I'm in, you know, Jose's Hangouts. I like the idea of taking the theoretical into the practical, and I like the idea of how do we actually believe in things that we can see and touch ourselves, right? And I like ways of validating things that we can do ourselves, right? Which are in our gift to do, not just trusting other people, which is like a lot of skeptics, yeah. I think the Earth is a globe. I've done enough measurements to be convinced of that, especially the story I told before, which we'll come to in a sec with some more pictures when I was in Cannes, and I'll touch on that again briefly for anyone who missed my story about Cannes. I'll go for it quite quickly. I'm keen to dispel sort of naysayers. I'm not a shill or an actor. I'm someone, at the end, you can ask me about CERN. There's lots of these conspiracy theories about Mandela effect, and they've opened up a black hole under CERN and all this kind of stuff. That wasn't my experience. I've been in CERN many times, actually. All right, a while ago now, they might have opened the black hole up in the last 5 years, but I suspect not. There was just a lot of very diligent scientists there. And I think it's really important that one gives witness to what you've seen, right? And I've seen that stuff. Not a lot of people have been into CERN, I guess. And you might never meet someone, maybe you will, right? But, you know, it's good if you meet and know someone who's actually seen something firsthand, and they can really talk about it firsthand, rather than it being all this stuff about the government and they're doing this and these scientists are up to this, that, and the other. You know, I can really talk about what I saw. Yeah, I can't talk about what I didn't see, but, you know, I can definitely talk, and I've showed some pictures here today with you guys of what I actually saw. I know the pictures aren't that stunning, but they are quite interesting, I think. And then I'm happy to have a one-on-one with anyone who thinks that they'd really like to know more. They're suspicious of me or something. You know, I know we get a lot from this whole actor thing. I'm not an actor. I'm not paid by anyone to be here. I'm giving up my own time on a bank holiday weekend in the UK. Okay, on to the next. Wrong way. Right, so I was a lot younger here. So this is kind of where I started out. Some people will have heard me on the Hangout before. This was about 1999. There was a really big telecoms and satellite boom, especially in the UK, but in America. And at the time, I think I was working for WorldCom, right? Verizon, which is a big American company, actually. And they owned a lot of stuff in the UK. We were involved very much with telecommunications and satellites, probably like a lot of people on the Hangout. You can see here a very old switch, actually, that we had here, which was powering this. You know, we had a lot of communications there. We also had a satellite receiver there, which acted as a way station and base station. And we were involved actually in doing some secure communications actually for government at the time here. And of course, so this is the roof that I'm on. You know, proves it's me. I mean, you don't know it's me because I've hidden the face. Again, I'm wearing a hard hat, different colored one this time. I'm on the roof setting up this tower. We're trying to get a beam from a satellite, and then we're trying to cascade some communications which had just come in, you know, which was the precursor to 3G actually at the time, these telephone masts. And we were trying to do some secure government communications across the city of London using line of sight, you know, and then relaying those communications. Yeah, great job, really good to get out there in the real physical world and touch things and go in. A lot of my world now is about management really, and I don't get to touch things anymore, but back in these days, you know, I got to touch and feel and look at stuff. Okay, here's the CAN fiasco, which I did touch on before. You can see me here. We actually got detained. So I was with the project team. I was leading the project team. We went out to Cannes. There was a big show going on. And the idea was, and I spoke about it before, we were going to get on these buses and we were going to track where the buses were. This was before smartphones came in, so you can see how long ago this was. About 2001 this was. So you can see some of you probably would have had a smartphone or cell phone that looked like that, or a cell phone. I think that's a Sony Ericsson, that's a Nokia phone. You know, these are really very old phones, right? But at the time, they were absolutely the cutting edge of technology. Smartphones did not exist. Yeah. What we were trying to do, we were trying to, on these phones, let the delegates at the conference know when they could get this bus. So we were trying to track these buses, basically. And I was out there all week. We had to power this unit. You can see here, there's a sat-nav receiver on the unit, a very old one. Here's the aerial of that sat-nav receiver that plugged into this bit. And then it actually used a mobile phone to actually ring up and get the data for the satellite measurements. Yeah. So it wasn't a smartphone, but it was actually using the phone to relay the data through a SIM card for a text message, basically. Okay. To power it, of course, we weren't able to power it because these buses, they use 24 volts, not 12 volts, and 24 volts would explode, you know, blow the kit up. So I had to go into a French supermarket, Carrefour or an Intermarché, and buy this battery, and then I made all this setup in this sort of car park. At one point outside the supermarket, the project team, the French police got very interested because obviously, I mean, in those days, right, there wasn't so much terrorism. I think it was even, you know, probably just before 9/11, actually. It must have been just about 9/11, actually. I can't remember the date precisely. But obviously there was an interest still in terrorism. And obviously people are walking around with stuff that looks like this. It does look a little bit suspicious even to me today. You know, who knows what that could be. So we were detained, you know, and had some explaining to do. And that was all sorted out. That was fine. The French gendarmerie let us go on our way. So we set all of this up. We spent a week doing it. It worked very, very well. It was very successful. We knew exactly where all the buses were. We had them plotted on a really big map, and we were sending out reminders to people, to the delegates, so that they could get to the buses on time, you know. And people ask sometimes, oh, well, look, all these satellites floating around in space. Why don't accidents ever happen? Why don't they get hit by space debris? I'm sure there aren't really satellites up there, that stuff. Well, I can assure you there definitely were satellites because we were picking them up. And then lo and behold, on the day of the conference, on the Monday morning, when we were going to impress everyone, you know, for the company I was working at the time, you know, we were going to get a lot of business off the back of this, and all these delegates going to this big IGC 84, I think, 2001 conference were going to get very, very excited about, you know, this technology we were showing. Didn't work at all. Absolute panic. And luckily we tested it about an hour before. Didn't work at all. Why didn't it work? It didn't work because you can see here this landscape here, these big hills. What actually happened is the satellites, all of the week that we were doing the testing, were in a, by the way, these satellites are not geostationary, right? They're actually revolving around the Earth. The satellites were in one position and worked perfectly, and we had line of sight across the sea on the satellites. Of course, the week, that Monday morning, of course, the satellites were all behind the hills. So we're only getting 1 or 2 satellites, which were being read by this device. And that wasn't enough to get a fix. And so we had a really, really big problem. which we solved in a very low-tone way. What I did is I got the project team and I put a member of the team onto each bus, and then each person on the bus sat with one of these phones, and they just texted through to the command center and said, you know, the bus is 5 minutes away, because they had a little map, right? So they knew when they were getting near to the hotel, and they texted it, and then the delegates got their text message. And the delegates thought that obviously we were using all this technology, but we weren't. We were just using human beings sitting at the back of the bus, pretending to be one of the delegates. So, but, you know, we got our thing and we did our show and we moved on. But it shows me really that it is quite fragile, and especially in those days, this was the early days of GPS satellites as well, that it was very hit and miss, and quite often you do get failures and things don't work out. But I suppose that's life.
This is great. That give you a little idea on how much technology have advanced in at least 20 years. That's incredible, for real.
Shocking, isn't it? You know, absolutely shocking, isn't it? Yeah. Because it does look really old now when I look at those pictures. So this is some of the stuff that I get up to now. This is a little bit more modern. Here's my, as the Americans call it, shop. I'd call it a workshop. You know, lots of stuff that I get involved in. There's a lot of precision instruments in there. You'll see in a sec some more of the precision instruments. Look, you can see there's a level there on the shelf. Here, look, you can see this. This is a micrometer. You know, here's a nice workbench that I've got. So this is a piece of work that I was doing. I'm doing some furniture at the moment. Actually, I'm trying to make a replacement for something that's broken, and there's a fine piece of furniture I've got, so I'm turning that on the lathe, and it's a little bit of you know, a shape that's going to, I'm applying French polish here. So this is to give you an idea. You know, I like physical things. I like you know, handheld things. Here's a prototype device that I was also making in that shop. It's got a lot of sensors on it. Unfortunately, I can't actually say what it's for because it's IP covered, but by all means have a look at it. You can have a look at this. This is a sensor. This is actually a spectroscope. It's absolutely amazing, this little thing here. It's tiny. It's like the size of a postage stamp. This is a spectroscope, so it will actually measure light, and it will measure the color of light, and it can tell you from the color of light. So if you, I don't know, lit a match above it, it could tell you that there was phosphor and sodium in the match that you lit from the light that came off. It's absolutely incredible device, this is, yeah. It's linked up to an Arduino repeater here. This is actually an alcohol detector here. This is it starting to mount it in the prototyping unit that we're going to test it in. And these are ultrasonic rangefinders, just to give you an idea of the stuff. I mean, I made this, right? This is all made by me. It's a prototype, obviously. Let's go on. Okay, here we have some stuff in the same shop that I saw. I'm also, you know, like to do, you know, making things, creating things, right? Which is why I'm very interested in the physical world around us. You know, here you can see quite an old computer, actually. So this is my workstation. It runs something that's called Mac. Mac is a way of running a machine tool. This is a rotary engraver, but it's also a milling machine. So it's a three-dimensional milling machine. It's a little bit like a 3D printer, but it doesn't really print. It mills things. You can see the milling going on here. I'm doing a sample here. And then you can see what I made with it. I made a set of cufflinks. So this was a computer image. It's a picture of Horus, which is, you know, from an Egyptian tomb, actually, sort of symbol from Egyptian tomb. Nice pair of cufflinks that I made. And here's some more test samples. Yeah, and it takes weeks to do this, by the way. This is not something you knock up in 2 minutes. It took absolutely weeks to work out the whole supply chain of creating an image, getting it the right size, how to mount it onto here, how to stick this down, and then how to cut it out. So
let me interrupt for 1 second. Welcome, Jesss Koslowski. I apologize for the misunderstanding in times. I'm glad you made it.
Not at all. Can you hear me okay?
Yes, loud and clear. I hope good. George can make it also too.
Yeah, right, me welcome. Too. Thank you.
Hi, Jesse. You're just in time. I've managed to filibust for long enough through some stuff. So great to have you here, because we're just getting onto your bit.
Yeah, it's all been good. I've been listening.
You have? Okay.
I just haven't been near my laptop, which I had scheduled to be here at 11. But it's good that you had the opportunity to kind of go through a lot of the basics. The Survey 101 type of presentation that you gave, I thought really covered it. It was
brilliant.
Good.
Brilliant. Yep. Okay, so we're just getting to the exciting bit where we get to your experiment. So I'll speed up a bit now that you guys are here. As I say, I had been filibustering for a bit. So here you go. Here's me trying to get an old, actually, satellite device. As you can see, there's a screen on it where you can like hack it a little bit, and you can pick up where the satellites are. Here you can see that there's 1, 2, 3, 4, 5, 6 satellites. I'm picking up 4 at the moment. I wish I'd had 4 when I'd been doing the work in Cannes, but there we go. You can see north, east, south, and west where the satellites are coming from. And I was going to try and do an experiment using copper sheets to try to stop the signals from satellites other than in one direction. We spoke about that on the panel, and I'll come back to that later. It's an experiment I'm looking at. This looks very dangerous, actually. It's an amazing picture, isn't it? This is uranium glass, right? Now, luckily, uranium glass doesn't actually give off too many, gamma particles, but it does give off some occasionally, sort of like 1 an hour or something. And what I'm doing here is I'm hitting it with a really high power argon laser, which is exciting it very much, and you're getting this amazing green glowing effect that you can see here. I've got some other pictures of this, that later on some other time I'll put together, but it's I've got actually some video of it as well. It kind of glows like it's kryptonite. It's an amazing experiment when you hit it with a really decent laser, and it's a thing called uranium glass. And by the way, you can buy it, right? You can go in charity shops, and if you look out, it kind of looks like Vaseline colored, right? If you know what Vaseline is, petroleum jelly. It kind of the normal color is this sort of dull yellow color. If you hit it with a high energy light source, it glows. Amazing experiment. And then here again, we get back to the ranging device. You can see the lux center on the top. The lake experiment, right? So the lake is used as an example to illustrate how we can build up observations that are informative. So what I've done is I've gone through obviously the 101, a little bit about mapping, a little bit about sort of, the world around us. And as Jessie said, sort of the basics of using W levels, theodelites and so forth, and a little bit of the history of how we created all that. I've gone through a bit about my credentials, my background, why I'm interested in all this stuff. Because obviously this session came around because of that hangout that I had with Mind of God and Ali B. They asked me to go away and come up with some material so that I could talk about it. In my research, I came across Jessie's work, and the lake experiment, just for particular reasons we'll get onto, I found absolutely the best example of any kind of experiment you could do, especially when looking at curvature, for the reasons that we will get into. And then that's why I put this together, and I asked Jessie and George to come on because, of course, it was Jessie's experiment, right? All I've done is I've added a few extra pictures. So we'll go through this quite quickly. Looks like a lot of words here, a very wordy slide. So the lake experiment, I'll give my bit, and then I'll ask Jessie to talk a little bit so that we've got the sort of toing and the froing now that Jessie's joined, and he can add anything that I've missed. So we're going to go through a step-by-step detailed summary of this experimental observation undertaken by Jessie, I think in 2016, if I got that right, at Cooper River Lake, New Jersey, USA. And I chose this experiment. Why did I choose it as a sort of illustration? First, I think it'll help everyone in the audience to understand how experimental work is really undertaken in the field. And Jessie has got some fantastic photos. And it helps earlier, I think, that I gave the visualization of some of the methods that are going to be used. So you'll understand from Jessie's photos what he's actually doing, I hope. And many of the techniques here could be applied to the CP or the Mind of God tests that we're talking about. And we're debating at the moment how we can come up with those tests. Secondly, I think these observations are very good. They're based on a very simple premise that water is flat or curved. Yeah. So by using the water as a baseline level, lots of external assumptions and dependencies are removed. So we don't need to know about R. Yeah, because we're starting from the essence that water is flat and finds its own level, or it doesn't on a curved Earth because it follows, it bends because of gravity. So the experiment becomes reliant only on the measurements that we take within the experiment. So we're not depending on radius or pre-existing glowed aspects that I know a lot of people get very heated about. We throw them out of the window. We're just dependent on what we can do within the experiment, which I think is fantastic. And then thirdly, obviously I'm on the panel. I've agreed to help move some of these ideas on so that we can try to look at an experiment. As I say, Ali B, Mind of God, and some others asked me if I could sort of capture some of these ideas and sort of visualize them a bit. And that's what I've tried to do through this deck, as you will see. And then I saw what Jessie had done, and I couldn't resist, adding that in. I've left the maths out, angles and calculations till the very end. As Jessie knows, he's seen the whole deck already. I'm not being snide. I'm not being a snob. I'm not saying flat earthers, don't like that. I just think that a lot of the people on the flat earth side are more what I call visual thinkers. They like impressions and they like ideas, much more sort of logical and mathematical. So what I've tried to do is I've tried to put a lot of the maths to the end. And I think this experiment is really good because I don't think it heavily involves on maths at all, right? You can visually see what Jessie is trying to prove here, I think, with the observations and pictures he's taken. And then finally, I think this experiment will help show how we can work with, between water and land. We can take observations. We can copy some of the techniques here, and we can use them in the physical environment. And then we can also use GPS, though GPS isn't really the main part of this experiment. I've sort of separated GPS out because I don't want to confuse people with the GPS aspects. And then, I think people can undertake this experiment themselves, and later on I go into what I like to do there. So do you want to talk through, Jesse, this piece about sort of what the lake test is and your approach?
Sure. Do you have a next slide coming up?
Has it not come up for you? It's on what is the lake test? It says observation, hypothesis, method. Is it not updated for you yet? Is it lagging a bit?
Oh, I was looking on the YouTube channel.
Okay, yeah, sorry. If you go to the main screen, there we go. It's come up now.
Yeah, without reading through all this, and anybody can obviously pause these screens and look at this later if they want to look at the additional details you've provided. But I'll say this: I did this I think it was in 2016. I had been looking at flat Earth for about a year. I got involved in 2015. The reason I conducted most of my early tests was curiosity. I just wanted to see for myself. That's it. I wasn't out to prove one way or the other. Obviously, I've been practicing surveying since out of high school, and I got out in '78, and my second job was surveying, and I pretty much have been doing that ever since. So, when I came across flat Earth, it piqued my interest to see if, I wasn't doubting, the surveying aspect, but what I'll tell people is that every day a surveyor goes out to do his work, he doesn't think, I wonder if it's still curved. Let's make sure. Obviously everything we are practicing is based upon, as Toady had brought out through history, measurement upon measurement upon measurement through decades and centuries. And this is how we've come up with the models that we use. And they just, and they work. And if anyone's interested in that, you can go back and look at the development of the practice of surveying over time. And, you'll see it begin like with the Romans. They didn't have theodolites. They didn't have telescopes with crosshairs in them. They used strings, plumb bobs. They used water as a level. They would make a channel in a block of wood, fill it with water, and put some sighting pins on that. So all of the basic fundamental operating aspects of how surveying works, are very old. And so over time, as mankind began to be able to machine things, you come up with improvements upon the old. So you start to see compasses being built. You see, you can fast forward to when the telescope was first invented, and then the idea of actually putting a crosshair in the telescope to point and aim, and then combine that with a protractor to be able to measure angles. So I'm jumping forward through time, but what you see is a refinement of the machinery, the equipment, the instrumentation, and but the basic premise of how this works is still there. It's still the underlying fundamentals, and that is that a plumb bob points down, and if you create a plane perpendicular to that, you have a measurement reference system that works quite well for building all sorts of things like bridges and tunnels and LIGO. The reason I included LIGO in my little talk there, or that little video, was to point out that LIGO is built tangent to the Earth. Those tubes are built straight. So if they had been just building tubes or a pipeline, like an oil pipeline or something, the tubes would curve. They would just follow the equipotential surface created by gravity. So they had to actually develop methods to combat that or undo that, so that those tubes would be straight, 4 kilometer long straight tubes, and set tangent at one point in that area. But anyway, I'm kind of shotgunning here. I'm giving you a broad idea here. So let's go back to why would I do this test at the lake? I just wanted to see for myself how a lake could serve as a level reference. And so, I just made the assumption, okay, this lake appears flat. if I set 2 points on either side of it at the same height in reference to the water, obviously I don't want to set my instrument up in the water. So when you see the video I made or look through my presentation, you'll see I set a spike and then, at 60 millimeters above the water. And then I used a carpenter's level to offset that back onto the land and set another spike at the same height. So now I have 2 reference points that are level with each other using only the lake, no instruments, no other means, just saying, okay, this lake is level. And now I have 2 points set in reference to that level surface. The next step was to set up my equipment. I set up the theodolite and I set up a target on the other side. And I made sure that those were set at the same height above the water. And then proceeded to do several things. One was just to take some pictures, okay? And I have to make sure people understand that when I take pictures through the theodolite or the level, you have to realize that those are not measurements. They are just me sharing, what I see personally when I look through that telescope. So it's not something we do on a day-to-day, practice of surveying. We don't generally take pictures through the telescope. Although, just an aside, we do have theodolites and total stations now that do record imagery, and we can use that in a photogrammetric sense, but that's a different topic. But so I did take this picture that is being shown right now. The crosshair is set 90 degrees. That is perpendicular to the direction of gravity at that station. And I wanted to see, well, what's it look like? And this is what I saw. And it's clearly slightly above the target. And I did the same thing on the other side of the lake, looking back. And the same thing is that I saw the same thing. And I took pictures on both sides. Now that was just for the visual representation. What I did after that was to do surveying procedures that you would use if you were going to be building a bridge here. And I used high order triangulation methodology, probably at like second order it was second order work, good enough to determine positions to better than a centimeter, better than that. So I took numerous repetitions of the vertical angles. And I did this in the morning, and I did it again in the afternoon. So I actually repeated this several times on both sides of the lake. And the result of that showed me that I was actually able to measure the tilt between those 2 plumb lines. I'll pause here, Toady, if you want to add anything, or the one thing I have to say is, like, I was very interested to see you take this work. You're the first person I've seen. Maybe others have, and I just haven't seen it. But you're the first person I'm aware of that took the work that I've just present and put out there. I don't draw conclusions from it. I've just made the measurements and put it out there to see if anybody, would take it, pick it up, analyze it, and consider it. And you've done that. And so I'm interested to hear you talk about it as well. It's just, it's not me all the time talking about this. It should be others examining it and, see what you think of it.
Yeah. So I'll add a bit, because we've we trotted through a few pictures there.
Yeah.
I think the really important thing for me, why did this particular observational experimental observations that you took, impress me so much? First of all, you started with the assumption. Yeah, and we had the whole sort of, scientific method bit that I put up earlier, but we started with the assumption that the lake was, well, one of two things. The lake is either flat or it's curved, okay? And we don't know which. We're just starting from the assumption, yeah, that we don't know which. Okay.
Agreed.
Then what you did is you didn't introduce externals. You actually went to that lake, and it is very calm water. We can see from the spike. So here's the spike picture with your rebar or whatever that you've hammered in. On the lake. It's a very, very calm lake. And we all know that water will take the shape of the container it's put in, and that will tend to be level. Now, what do we mean by level? Well, we'll get to that, but it will take the shape of the container. So you've got a lake, there's no waves on it. We can't say that there's wind or waves obscuring it. It's very, very calm. And what you've done is you've stuck, obviously you didn't want to put your measuring devices in the water, as you said, but you've taken here a known height, and we can actually see that spike going in here. And you've taken that and you've measured that. And then in the next sequence, let's go through them. What you've then done is, as you said, you took a level and you worked back from the water, 60 centimeters above the water. You worked backwards, you made a level, and you made then another spike. Yep. And then you called those two spikes. You did this on both shores. So what Jesse has done is he's basically got two little mini platforms on two different shores of the lake, which are about, I think, 700 feet apart. Okay.
I'd just like to interject one thing here at this picture. When I posted that video, back up one. When I posted the video showing this, by the way, if you watch the video, you'll see this in action. I'm holding the camera in one hand and banging the nails in with the other. So you'll see me putting that level on there over and over until I do get it to be level. But the comments that I got back then in 2016 when I first put this up was how inaccurate this is. And this is so inaccurate because they felt that if these two nails are not level with each other by some small amount, that would project across the lake. And this right here, and these became nasty, hostile comments that I'm a fraud and this is ridiculous. And I really had to point out to them. I said, look, think about it. This level this carpenter level sitting there is as level as you could hang a picture on your wall, or install a window in your wall, or anything like that. That's the accuracy we're talking about here. And that this is isolated to this side of the lake. It doesn't project across the lake. In other words, if these two nails were out of level by an entire inch, that inch doesn't show up magnified across the lake.
Yeah, I think they've misunderstood.
They're misunderstanding.
Exactly. They have misunderstood that starting point. And that's why I think I put the, the 101 stuff we went through about the heights and measuring from and to a height.
Yeah.
Yep. Because.
But I introduced that here at this point so that people hear, it's like, if you're going to criticize the experiment or this measurement method, be sure of, you can't make, you're just showing that you don't even understand these concepts if you actually think that any misleveling in this 3 feet is going to be magnified in the 7,000 feet. It isn't. It's isolated to this point. So
yeah, if you're a centimeter out here, you're going to be a centimeter out on the other side. Yeah.
Correct.
Yeah, that's it. It's not going to be magnified over the 700 feet. Absolutely.
Correct. That's correct.
Yeah, and I think the diagram shows that later on. So we'll crack on through a few of these. This is obviously showing that it's level that I'm seeing. I don't know if you're seeing my screen. And then we get a really nice side shot of it, which I think is great. It shows how we work back from the water, because I think with the talking to CP, Mind of God, we're talking about practical methods of bridging between water and land.
Right.
And I think this is great. It shows it's doable, right? It shows to me it's doable.
Yeah, and it's not unlike anything we do when we have to build, let's say, a bridge, and we must make sure that the lowest deck of the bridge is going to be a certain height above mean high water. When they start calculating ship sizes that are going to be coming through that channel. Well, all the work that is done is referenced to tidal benchmark stations on that construction project. And it's a very similar idea. It's like you've got a tide station with a rod in the water, but nowadays it's done electronically with an actual mechanism. But we used to just read a rod fastened to a piling, But this is the same idea. Any work along water that you must determine height differences in relation to that water. It's just the same idea. And here it is, a very simple picture showing a carpenter's level, bridging it back out of the water.
Could you just talk us through this one, Jesse? Because I know we're going to get some comments about lasers. Could you talk us? This is the target, I presume.
I'm glad you brought that up. So yeah, this is a retro reflector. You could see my face in there upside down. in the cubic prism. You see that?
Oh, yep, yeah, I can see it. And a phone. You're holding a phone, I think, taking the photo.
Yeah, I'm taking the picture.
Yeah.
So, so this is used with a modern total station instrument to measure distances. And people are calling that a laser. That's fine. It's in survey terminology, we call it an EDM, Echo Delta Mary. It's an electronic distance measuring instrument. It's actually EDMI, EDM for short. And they're infrared. There are different types of these, but it is a light type of a system to measure the speed of light across. So the total station fires out a light beam, hits the corner cube reflector, it bounces back and is received at the total station. Divide the time by 2, you have the distance in meters. You can convert that to feet. That is that has a limited range on it. The early ones, the ones that came out back in the 60s and 70s, possibly the 50s, I'm not sure, but I know in the 60s and 70s, these things could measure 100 miles. And I became friends with one of the guys who did the very, very long range distance measuring at the McDonald Observatory. And they were using a geodometer. They called it Big Red. And that thing could measure, I don't think they ever found the limitation on how far it could measure. I think that as long as you had enough obviously they weren't measuring to one corner cube. They had a massive wall of them, and they could measure, very accurately to 100 miles. And but commercially, as EDMs became more introduced into the surveying profession in the 70s and then the 80s, of course, there's really no need for a surveyor to need to be measuring hundreds of miles. That's a very large instrument. It's expensive. Your day-to-day practice, if you were measuring several miles, and I'm talking pre-GPS in the 70s and 80s, there was still a need to be measuring, even in some cases, tens of miles, okay? In combination with your triangulation and traverse, your angle measurements, right? As GPS became introduced into the profession and made, it became something easier to use, and you could survey very long distances without any limitation because there's no line of sight requirement. You can measure from one side of a mountain over to the valley on the other side of the mountain without any need to see between. So the EDMs became more limited. So today, if you buy a total station, it may have a range on there of only several miles because it has no need. That doesn't mean that you could not still get an EDM that measures very, very far. Right. Now, that's just a little bit of explanation on some of what I've been seeing about a new topic I've been seeing floating out there in the flat earth community is, these instruments are limited. You're using them beyond the limitation. And I think they're confusing the angle measurement capability with the distance measuring capability. And you can find out for yourself the specification of any instrument. You could look up a Trimble S7 instrument and look at the brochure and look on the back, and it has the specifications of how far it can measure distance.
Yeah, Jesse, I actually have my TopCon manual.
Yeah,
that
so
I bring up and show people the specifications for distance measurement as a function of the number of prisms that you have.
There you go. And so what happens is, people have to become aware. Like it's sort of like the guy saying, "Hey, your level's at a level in 3 feet." Well, get deeper into what it is you're having a question about and find out. Oh, I see. The limitation is on the distance measuring, not the angles. The angles, so long as you can resolve the target well, you can measure angles out to 10s and 20s and 30s of miles. You can measure to a radio tower that's 20 miles away. You can measure those angles as long as you can resolve the target. And it's no different than, say, a telescope on a rifle. You know, you're going to dial that telescope in as you practice on the range to assure that you're firing and hitting your target. It's the same thing with a theodolite. And this is where I'll go back. I think I'm looking at
Jessie.
on here. I just want to finish this one slide, George, and then go back to that slide with the prism. I don't know how
Am I not on it?
There it is. So now, just so everyone understands, in this test, in this lake measurement, I did not measure the distances with an electronic EDM.
Yeah, I wanted to add that because actually it's irrelevant almost the distances when we get to your result. I mean, not that you didn't measure the distances, but actually the distances when we get to the shocking conclusion, right? It doesn't actually matter how far it is.
So but I went into that to get to at least give the sufficient detailed information that people understand. There's certainly a limitation on an EDM's range, and you can buy EDMs as much money as you want to spend to go farther and further. Generally in practice, if we can measure 1,000 feet with an EDM accurately, that's pretty good for most of the work we do. So in this test, it was all about the angles. And that reflector, I'm just using it as a target. So don't be confused by the fact that there is a corner cube reflector there. I'm not using it. I'm only measuring to the target, and I'm measuring the vertical angles.
Yeah, and I don't want to confuse people because I think we're talking about broad topics here, aren't we? In this lake test, what Jessie did is he got some levels on each side of a 7,000 feet lake. Yep, he made them the same level because they were level with the water, and then he put targets, obviously, and surveyed from both sides. Yeah, each way. Yep, from a target on one side and target on the other side.
Right.
And in theory, if that lake was truly level and we were on a flat Earth, then those two sightings from each end, just like the diagram I showed earlier, would be exactly level, horizontal with each other. Yeah, that's
right. And then
undeniable.
of course, exactly. And the next thing that came up back in those days was perspective. It's lower because of perspective, but nobody ever came forward with an explanation on the rate, because I would always ask, at what rate does that change over those distances? Do you have a model that describes this and could predict it? And of course, it doesn't go that far. And to me, if someone's really searching for the truth, you're going to explore this fully as far as you can. But what seems to pass for, to refute this is just simply say, that's perspective. And people who are happy just to hear that and accept that, you got to question, really, how interested in the truth are you? This is not perspective, because obviously, like I said, I took the picture through the telescope, and that's just a picture, just so you can see what it looks like. But I went on to measure multiple zenith angles with resolution. I forget, the standard deviation was down in the second or two. It was very, very small.
And these are the techniques that we use to build all the things that we went through earlier. I think it's an important point. Yeah. Yep. What I like about this, because Mind of God is pinging me, I think, in the chat saying, are we going to get onto the actual, his ideas from experiment? The reason I've gone through this, and we'll crack on through these pictures. Here's a really good picture where you can see that obviously the target is below that horizontal line that we showed earlier. You can see here, isn't it? It's a really clear picture, isn't it?
Yeah, and here's the stats. The stats on here. I've got the zenith angle, and the standard deviation is under a second. Standard error of the mean is 0.3 seconds. So, and again, was repeated in the morning and then in the afternoon.
So even if there was a temperature or there was differences during the time of day, you were trying to get rid of those issues, yeah?
Not so much get rid of, but discover. Like I said, I came out here with pure curiosity, didn't build anything into it other than establish these 2 points level with each other, then proceed to make these measurements and find out what it looks like. And, at different times of the day. And I've done this test more. This is the one I presented. I've done it I've done this on land,
Mm-hmm.
and I've done it on another lake. And my most recent testing has been only several hundred meters, like not far,
Mm-hmm.
really,
Mm-hmm.
very close. In other words, eliminate any possibility of atmospheric effect, because when you set the target up about 200 to 300 meters away, you can see it clearly with your naked eye. I mean, it's like right there. There's no variation. And I do have to say, to criticize these tests that are being done to, very meticulously and very carefully, and then I compare it to some of the things I see where people are putting cameras down at the water level or down along a railroad track, and you're like inviting the worst conditions possible. I mean, and what is the point of that other than to say this would be a very bad time to make any measurements? And I'd like to get across this too, that if anyone's interested, you could just search on triangulation tower, and you'll find out that back in those old days, they literally erected towers 60 to 100 feet in the air in order to make their triangulation observations out to 10, 20, 30, 40 miles. The longest triangulation observation is from Mount Helena to, what's the other mountain? But it's about 195 miles over there in California. That was done in the late 1800s, early 1900s. So it's possible to see very far to a point. And, you can measure those angles because what they used for targets were heliotropes, which is a device that enables you to measure or reflect the sun back toward the instrument observer, the instrument operator. And, you get a nice pinprick of a light that you can just aim on very precisely. And then, of course, at nighttime, they would use a light, a very high-powered light. And when you're looking at that from 10 to 50 miles away, it's a teeny tiny target, and you can resolve on it over and over. And they took 16 positions, 16 rounds between all these. So angle measurement has I'll say it this way very simply, and then we can move on. The limitation on measuring the angles horizontally and vertically is only this: can you resolve on the target repeatably? In other words, if on one day you're looking at a target and the atmospheric conditions are very poor and the target's moving around a lot due to turbulence in the atmosphere, you're not going to measure that target. You just say we can't do it today. On another day, it's all clear, cool, crisp, and you can see it very well. You can get that measurement made. So it really does come down to your ability to resolve on the target and then to take repeated measurements to it that satisfy the requirement of the project that you're trying to usually build. You're usually trying to build something,
Hey, Jesse, it might be a good point here to point out to people that we generally specify angle measurements two different ways. You can either put it in decimal form or you can put it in terms of degrees, minutes, and seconds. And for those that aren't familiar with the terminology, a minute is 1/60th of a degree, and 1 second is 1/60th of a minute, or 1/3600th of a degree. And to put that into perspective, the resolution of an eye is generally considered to be about 0.02 degrees, which is 72 arc seconds. So when we're talking about a second, you're talking about resolving capability that is better than the human eye by a factor of 72.
And so what we just walked through is, because I can see there's a lot of chat of this is ridiculous, it's just sticks in the ground. So what we've done is we've seen Jesse's, exactly. Jesse.
Well, here's my answer.
Calm down. It'll be all right.
Just one. It's a very simple thing. Of course it is, and it will always remain that for you. Have that. You see, there is no convincing someone who doesn't want to actually evaluate, you know, and the thing is you could ask them, do you drive across any bridges? Do you go through any tunnels?
Exactly.
You know, just think a little bit about what it took.
The world that you live in, which is,
Yeah.
that was the context I was trying to show earlier, right? We've got a world where we do this stuff, right?
Yeah. And so we are, you know, we have a wide range of people in this community. And you know, I'm more interested in speaking with people who are actually willing to consider, you know, the reality of what we can do here and what's doable and what they can do. Look, not everyone can buy theodolites and so forth, but there's other things that can be done with just sticks and string and weights and protractors. And
exactly, you can make your own clinometer.
You know, put a sundial in your yard. You know, just get a sundial and put it in your yard, and then think about, how is that working? Why does that work?
So what we've done here, I'll try and get to the picture here. The panel will want to come in as well, right? So I'll just, sorry, George.
You two tend to be much too diplomatic. I mean, there are some really profoundly stupid people that watch these videos. I mean, there's guys in the chat like Ute and Gamer Tamer. There's been a recent one calling himself Boom and a few others. These people are, I think they willfully do not want to learn anything.
Oh, let's not worry about them. Let's worry about people who do want to have a conversation.
The thing is like where this started with about the limitations of a theodolite being confused with its distance measurement capability started, I think, with Ute or someone out there. These guys, this is just kind of a recent development, and they don't know how to read the specs of a theodolite, and they don't seem to understand that the measurement capability does not affect the optics whatsoever. It's decoupled from the optics, and trying to say that your theodolite is limited by the distance measurement spec is like saying, say you have a personnel carrier that you know can carry people out in the field 10 miles, 100 miles, limited by how much fuel you have in the vehicle to carry people. Now you're going to mount a 50 caliber gun on there that can shoot a mile. Now all of a sudden the carrier is only capable of going a mile because of that gun on there.
Sure. So what we've gone through here is we've looked at Jess's very, very rigorous multiple different times of day measurements. We've gone through very quickly the use of GPS, and GPS is just using here as a comparison, right? It's not a fundamental part of the test, okay? The data is here. So just, you know, getting to the point that Mind of God made, yep, there is an ability to match GPS, and lo and behold, it's quite surprising, but the GPS measurements do actually match the measurements that were taken, you know, from the surface of the lake. They're all consistent. You can see the measurements here. And what I want to get to is really this picture, right? Because for me, this is the clincher. Because from the evidence that we just seen and the data that Jesse collected and the video that he made that you can all go and look at, all right, what did he do? He took water. He took the water to be theoretically level. We don't know if it's bendy or not. He did exactly what you see here. He got his carpenter's level. He made two little sort of, points. He worked back from the water to have a point. He then made two straight lines, you know, using that level. And in both the pictures that you've seen earlier, it fell short, right? So therefore, it wasn't exactly level. It wasn't pointing exactly level with that target that Jesse showed there.
One piece of information to add here. This is a good picture to describe it. For the criticism that was brought up, that let's say on the right side, let's just say I had one of these nails was down an inch. All that would happen is the thing would be lowered by an inch. It would not change the deflection because the instrument determines that.
That's correct. You're only using it as a point. Yeah.
You see what I'm saying? So even if my nail was, I even told the guy, I said, what if I couldn't level to 1 whole inch?
Yeah.
I was that bad, or I stepped on the nail, you know, whatever. It would just lower it or raise it to that. It would be isolated there. But these lines that you show intersecting out there would be in similar fashion. Okay, I just want to make that point. So it doesn't. I don't want to hear that come up anymore. It's just dumb.
Yeah. It's a nonsense, and we can explain it with one of the earlier pictures, which I show where people are measuring from the point below. So just so everyone gets that, Jessie didn't do what I've sort of shown here, because I'm just trying to show the concept. He didn't take his measuring his level, and he didn't put it on top of a little platform that he'd built, you know, on top of that. He's just measuring from the top of the point of that nail.
Hey guys, I might point out, keep
concept.
this diagram up,
Yeah.
because this brings to mind a very simple, easy experiment that can be done using 2 auto levels. And auto levels are fairly cheap on eBay. You could probably purchase 2 of them for under $200. And if there were people out there that were truly interested in making a precision measurement to demonstrate whether or not the Earth is curved, you could take 2 auto levels, separate them by a couple miles like you have here, near a body of water. You make sure that the optics, you're on a calm day, and that the optics are the same distance above the surface of the water, and aim them towards one another. Now, if the Earth is flat, the crosshairs in, say, the right auto level will be sighting the scope on the left auto level, and vice versa, if the Earth is flat. If it is not flat, you'll be getting what you see in this diagram with a curved Earth. Each auto level will be aiming high above the other auto level.
I can see the panel will be exciting. There's lots of people in the chat saying that.
Yeah, the Rumpus is hot in the chat saying that Jessie is wrong.
Let him. We're nearly at the end. Okay. Then we got some little proof. Yeah. Then we've got Jessie's calculations. Okay, which show essentially what we saw. I think that the important thing is we took a site. You can see the site, and you can see that it's above the target. Yeah. Of course, you can work through this, and so no surprises. This is consistent, of course, with what you'd expect, right? One arc degree and so forth. Yeah, you know, you can see the calculations here. People can take screenshots and work through it. You know, so you know, my summary is that I think, and Mind of God is asking me, why did I put this material up? I put the material up to help everyone understand that we've got a physical built world, to understand a little bit about how we use levels and how we use these simple tools. We're not getting confused with EDM and those other aspects, right? Because people will start to throw, you know, stones there, as it were. All we did is we took some water, we took a couple of points, and we took something that was level, and we took some sightings with it. Now, I know Rumpus is going to come in and talk about refraction, right? And it is a potential factor here. But again, with the measurements that Jessie took, with the calculations you can see, you know, within the margins of error, which are there, we know that we've got some margins of error, some deviations. We found what we expected to see, right? And Jessie didn't enter the experiment trying to work out what those values were. You know, he did the experiment, he did it accurately, he recorded the results.
Before we get all caught up in refraction,
exactly,
is we can monitor these things over days and weeks and pick days in which refraction is a minimum.
Yeah, my suggestion is, right, that you know, once we understand what experiment you guys will do in the US, yeah, I think it would be really good that we'll do one in the UK as well. You know, I'm willing to put a little bit of money to hire some, you know, a theodolite and some levels and some equipment, right, and go with some flat earthers, and we'll do a test in the UK as well. So we do a couple of tests once we understand what the test is. By the way, I think this experiment is an excellent one. By the way, I think it's really good.
The thing about refraction is it's there. But it doesn't explain all of what you're seeing, and it can be accounted for. And you know, that's why.
An experienced surveyor and geodetic surveyor, such as yourself, learns to recognize low refraction and high refraction days from experience.
I think the whole history of how we come to model refraction is interesting in itself, and it's deep. The whole thing about refraction, as it became, you know, as they were discovering the effect of it, it came about through a combination of everything you've looked at here today. They did lots of leveling. I mean, and we're talking high precision leveling up through mountains. And this was done in India, the United States, Europe. Lots and lots of good differential leveling to determine the actual height differences between points. And when they do that high order leveling, the sight distances are they're not even 60 meters. They're very short to eliminate the possibility of refraction being in there or minimizing it greatly. So you end up with very, very well-determined height differences over many, many miles. And then what do? Well, they occupy them with theodolites, non-distance measuring theodolites, just instruments that measure the angles only. And they measure those vertical angles repeatedly over lots and lots of time. We're talking decades and centuries of these measurements. And they begin to see the differences between the vertical angle determination of the height difference and the highly precise leveled difference. And they can then begin to model that effect. Why? Well, because when they did the vertical angle measurements, they were measuring temperature, pressure. So with all of this data, and we have hundreds of years of these measurements, you can do some analysis, and it has been done. And that's how we come up with the coefficient of refraction, the standard, values that are used. And but I have a lot of links to papers where they've done lots and lots of testing, even in the last several decades, to even refine it further. So Walter Bislin, his blog page has probably the best collection of all of the information about refraction you'll find anywhere, and easily presented, easy to understand. It's quite good. So yeah, there's refraction, but
I don't think it's explaining away all of that height difference that we see.
No, of course.
And if it was all refraction, then we'd be very confused because we wouldn't be on a curved Earth, and the various other bits of evidence wouldn't then link in, would they? If all of it was due to refraction, yeah, there's quite a considerable height difference that you've got there over that. That's
the practical aspect I do try to bring to this, is that if in fact this is all wrong, how is it that we get so many things right?
Exactly.
How is it that these tunnels and bridges and skyscrapers and just all of the construction around us, plus the maps? I mean, let's face it. If you're going to quote the heights of lighthouses and the locations of lighthouses and mountains and so forth, where's that information coming from? It's coming from a topographic map that some surveyors did the measurements to determine those positions and elevations. Are they right or wrong? Let's get real here.
All right, let me jump in 1 second. I really want to thank you very much, Toady Liley, for putting the effort and time to do this presentation. It was excellent. People loved it in the chat. We got the usual trolls, but a lot of people heard the information. I hope they took notes and they listened to it carefully, because it was a lot of very cool details to talk about here. Thank you, George Natiuk and Jesss Koslowski. I apologize for the misunderstanding on the times that we brought this down, but yeah, it went down really well.
I think it worked out fine, Jose. There was a little mix-up on the time, but it gave Toady a chance to go through a lot of the preliminary information, and I was happy to join at this point to add a little bit. But Toady, you did a great job, and I want to thank you for even considering the data I provided to.
No, you're welcome, Jesse. As I say, I was researching the whole thing, and Mind of God will join the panel, I'm sure, and have some questions to me. This is part one. Right, there's a part two, but I wanted to get the baseline for everyone on the panel so that we all understand about the equipment and the observations and how we can get a straight line in the real world.
Yeah. Now, really quick. This is kind of the wrap up of the main presentation. I'm going to share the link on the side chat, so everybody is welcome. Please, when you join, do not talk over each other. Please be civil, and let's go to questions and answers. Let's just please be adults and not start shouting and yelling and over talking. Carry on, guys. I'm going to share the link, and hopefully it all goes well.
Yeah, let's hope so. Thanks, Jesse. Thanks, George. I'm sorry about the timing.
It's fine. It all worked out.
It worked out well. I suspect I'll get some questions about the whole CERN stuff. And I showed some really nice pictures earlier. I don't know if you saw. I think you saw them, didn't you? You saw the thing I did the other day where I shared the images of LIGO and all that good stuff.
Yeah, I did. I was able to watch some of it as I was
driving back. Yeah.
Yeah.
I will be silent. Yeah, welcome, Dean. You're the first one, but I'm gonna stay on mute. When people join, I will let you introduce yourself and take over.
Yeah, guys, I just want to say that was an absolutely fantastic presentation. It made a lot of sense and should have made a lot of sense to everybody. So thanks for the effort.
No, you're welcome, Dean. Thanks for that. I think it was, I saw Jess's video, and then I got some of the concepts. It takes a little while to think about it, and I wanted to try to simplify them for people so that everyone could understand that it was a very simple experiment, right? It didn't need, we went off into EDM and lots of other stuff, which is great, lasers and goodness knows what, but actually this just needs a site, a level, and the assumption that water is flat or not. Yeah. Which is why I picked it, because Jesse's got some, actually on his WordPress site, he's got a fantastic site with lots of pretty extensive observations, which I must thank him for.
Jose, don't let this Earth guy destroy this Hangout as he does other ones, please.
Well, the main thing I say is that just let the measurements speak for themselves. Think about a test you want to do, and then conduct it, and just do it as carefully as possible. Do it in a controlled way. Hey, Rumpus, and then you have a set of data that you can examine. You may choose to repeat the test again under other conditions, but start to look at the data itself. It does no good to perform photography and videoing in the worst possible conditions and then determining that, or saying now you've made a determination. It's like, no, you can't even measure that. And, obviously surveying is all about making measurements. Most of the things I see out there don't involve that. It's all about P900s, producing blurry videos. I don't know what you can do with that.
All right, hey, brother, I have a question for you. Can you hear me?
Yeah. Are you talking to me or?
Yeah, all of you guys that talk about CERN, that you were talking about how that perfectly level circle, 27 miles.
Yeah, I think I said it needed to be level and it needed to be an accurate circle. I didn't say it was perfectly level.
So,
yep.
Okay.
Instead of level, it's actually
it has to be perfectly.
It's straight. They have to make
straight. Okay, so it has to be perfectly 27-mile straight, like a coin, right?
Yes, like a coin. That's right.
Fantastic. Okay, now, so I'm assuming that the center of that perimeter must have a higher elevation, correct? And around the perimeter is supposed to be low elevations because
I don't know the design specification of where they set it tangent, but LIGO I'm familiar with. That L-shaped arrangement of those tubes.
I'm talking about the entire perimeter, sir.
Yeah, the perimeter, again, you'd have to look at the design specification, which we could probably look it up. I just never have.
No, it's very simple. Can I give you a little tip how to do that?
No, do you know the CERN?
Yeah, I know everything about it, sir.
Okay, so where did they set the tangent point?
What do you think I'm talking when I'm talking about the center of 27 miles? What do you think that is?
It'd probably be the center of the 27 miles. Like the center of the coin. Let's use the coin example. I like your analogy to a coin. Okay. So it'd be the center of the coin, right?
The center of the coin is supposed to have a little bulge. They just made a rim. They made a rim. Not they didn't build the entire 27 miles completely flat like a coin. They did only the rim has to be completely straight and level. Therefore, the center must have a little bulge to demonstrate that we are on a ball. So if you could put your Google elevation tool in the center of that 27-mile CERN and determine if that elevation, according to a topography map, is actually higher than the perimeter around CERN. I dropped my question. You should.
Yeah, so it is, but the way they dug the tunnels, right, it took them many years to do it, and they did it from a number of different directions using a number of different tunneling machines. And then they had to level the tunnels once they'd actually dug them. I mean, you saw my pictures. It's an amazing complex. It was very complicated to build it. I think it was about 12 years under construction. And you can still see the entrance points where various of those machines went down. I was lucky enough to go and visit those. It was a very, very complicated endeavor. Of course, in the middle of that 27 kilometers, I think it is, not miles, there is, of course, a bulge of the landscape. But since it's 100 meters under the landscape, I don't think the fact that it flexes up there is too much of a problem. I'm probably misunderstanding the question.
But doesn't it make any logical sense? My question?
Do you want to make a point, maybe, and the point can be addressed? I think it's easier than the question. Earth.
Well, the point, yes, the point is that by law, according to your doctrine formula, what formula are you working on? Because according to the formula they're giving us on the doctrine of the glove, we are supposed to expect a bulge in the center of that perimeter.
Okay, I don't understand the question.
I don't know that anybody sitting here right now on this panel can just answer that. So how about if we do this? You've raised an interesting idea, and it is something, like I said, I haven't looked into the actual design specification. It must be there. It's out there for LIGO. So now you've piqued my interest. How about we do, I get to go, and maybe anyone else here who hasn't looked into it, we go look into that and talk about that another time and find out,
okay,
where did they design just from what I know about LIGO and the need for that to be straight, I'm going to assume, this is an assumption, I'll find out later if I'm right or wrong when I look into it, that this thing had to be straight and it has to be tangent somewhere. And they have to design that and then construct it in accordance with that design. Just like anything else we build, bridges, tunnels, everything else. You come up with a design, then you have to make it real and put it there, like a pyramid.
Hold on, Earth, you see yourself flat. I think that's a good point. You guys, just take time because you're asking a question on the go, and it needs to be researched a little bit before. Welcome, Luis, and the Rumpus. I see you were hot in the chat saying Jesse was wrong, and I was like scratching my head. What's going on here?
What?
Did you see my picture as well, Rumpus? Did you see my picture at the end?
Yes, I have some serious questions, but I'm being persuaded not to pursue them.
All I'm saying is you, Jesse, and I can discuss this in private regarding some of the theory and stuff. I don't think it will serve any purpose to a lot of the people out in the chat. They're not going to understand the mathematics.
So I'm probably...
You sure, George? I mean, well, can you give us just a broad idea?
Okay, go for it.
Does it involve the refraction?
Right.
Yeah, whatever.
Right. Okay. You don't know what you're in for.
No, we do. We know what we're in for. I did think about putting a whole sequence. I've got 27 slides on refraction, and I put them in for Rumpus, and then I took them out of the final deck because...
right. No, it's not that... A refraction, I do believe, is an issue here. I mean, what's the distance?
It's not much of an issue. When I looked at it, I assured myself it wasn't enough of an issue to be a problem.
I'm glad we cleared that up. Now, and also, Rumpus, I will tell you, I did get, if you go back and look at the videos I've put out there where I've done this over land and over water. And when I did it over land, it was just curiosity for me. What happens if I measure the vertical angles over a mile? And lo and behold, I got about a minute, which is what you would expect, a 1 arc minute per nautical mile. And I didn't even lay out the mile. I just said, here's 2 mileposts of a highway. I didn't even measure that distance. I just assumed, okay, they must know what they're doing when they put these mileposts here. I come to find out they're not that accurate because later I did measure them. But anyway, I took a lot of heat, like, oh no, you can't do that over land. You got to do it over water. So then I did the lake test and I thought, well, this is cool. I'll just use the lake as a level and proceed. Did that. Now, both of those are you get a lot of interest about refraction. And so then I thought, well, what happens when you do the same type of measuring scheme, but very short, 500 feet, let's just say, just a couple hundred meters, let's say, and you can clearly see that if there's, obviously refraction is still there, but it's so minuscule over that distance, and the target isn't moving. It's like it's right in front of your face. And so I have those tests as well, and I think they're actually more interesting. And maybe at some other point, we may start to look at some of those. I have very good data sets of very short distances where the tilt between the plumb lines is still apparent and able to be measured and corresponds to the difference in latitude and longitude between the 2 points. That's the thing I've been trying to get people to recognize, is that latitude and longitude are real and they are measurable.
Right. The actual point I was contend, I'm afraid, is rather more serious. You said it's about the act. You were claiming that you're 1 centimeter. I've got a diagram.
I threw it. Did I ballparked a centimeter? What was?
No, let me just.
While you pull the diagram, Rumpus, let me get some mic checks over here. Some people that
the area
haven't
being
spoken.
cascaded out over the lake. Yeah.
Let me get a mic check from Khaled. Khaled, can I get a mic check really quick over here? Louis, mic check.
Yep.
Yeah. Hear you. And who else didn't speak? Laurie, mic check. Okay. Carry on, guys.
Do you understand, Rumpus, that we weren't using a level platform? Yeah, we were just using the top of it. I know it's the way I drew it. I tried to simplify it, giving the audience.
Your diagram was to just get across the concept of
exactly
setting these 2 points level with each other, setting these 2 points with other, and then the actual perpendicular plane is established by the theodolite.
Yeah. So, can you see my diagram here? This is what you were saying, and you said that if you got the height here by 1 centimeter wrong, that would only make a difference to 1 centimeter to your perceived. We didn't quite specify what it was. It was about 1 centimeter out, but the point is, if you do have a 1 centimeter error here across 1 meter, that will, if you're measuring across, say, 500 meters, the difference at the other end will be 5 meters.
But that's where you've misunderstood.
Okay, please explain to me.
Right. So I'll try and explain, then Jessie can absolutely tell you. But this is why, so it's not actually resting on a little platform. So if you actually looked at the way that Jessie did it, all he's doing is he's taking the measurement of the base of the theodolite instrument that is level from a point that is above that second. So if you go across with your little mouse pointer to the left, to the back one, that back one, exactly. Imagine that's a point. All Jessie is doing with that carpenter's level is saying, I have a level point of a known height above the water level for that back one.
But it's not level if this is 1 centimeter above that centimeter.
Yeah, so it's a centimeter out, or even an inch, as Jessie said. But then he's taking his level theodolite measurement above that. I'll let Jessie explain it, right? Because obviously I'm not making.
I may have misunderstood this.
Rumpus,
correct me if I'm wrong.
Diagram? Is this your diagram here?
This is my diagram.
Okay, look, your diagram is accurate if that's how we did it. But
you made the statement in theory that if this was 1 centimeter out, that in other words, this level across 1 meter was out by 1 centimeter, it would only make 1 centimeter difference at the other end. That cannot be correct if that's what, unless you did something else with the.
Just listen to me. Your diagram is correct if we did it that way.
Okay.
That isn't how we did it. So
okay, so how I misunderstood?
Because you show the instrument on top of that platform that has been cocked by 1 centimeter, and therefore the line going out is going to grow just as you're showing it, but that's not what's happening.
Oh, good. Was you saying the theodolite was used its own compensator?
Correct.
Oh, right. Okay. Okay.
If I'm
okay. That's fine. Yeah. So you didn't say that. The way you drew it, the way that
the way I drew diagram, my fault.
It was implying it was coming at it. You were using that to define your horizontal, but obviously, if you're using the theodolite, which to generate your horizontal, then the issue indeed is as you say.
So I'm still happy you've shown this.
Should have used a piece of wood.
This diagram here is the criticism that was being described in the comments under that video, and pretty heatedly. And I try to make the point that even if I set those two nails, if I did such a poor job with using the carpenter level that I was out a whole inch, when I set my theodolite over that point, the inch is isolated to that side. It doesn't grow. It doesn't affect
because it is the compensator. Yeah, indeed, the compensator. The theology is just the way that the diagram was drawn.
Yeah,
it was dependent on the level, and I was thinking, hold on, were you relying on that to get your horizontal, which is what was implied in what Toady said? But as you say, if you're obviously using the thing, then obviously,
the whole thing here that goes on is it doesn't matter what the tripod rests on, because the leveling base of the theodolite or the auto level completely takes care of any leveling.
And just
but
to
that's
bring
not what was in the diagram.
So Rumpus, can you see my screen at the moment?
Hold on, let me.
I'm trying to share mine. If you click on me and you can see my screen.
Yeah.
Yeah, I don't know if you missed this bit. You might have joined a bit late.
I did see this bit, but that wasn't this was a different. And I appreciate how compensators and the theodolites work. They have their own things.
So that second pin, the one at the back that I'm talking about, can you see where I'm putting my little cursor around? Yeah, and then you've got the whole level. In this example, Dumpy level, I think he had a theodolite. Yep, is all based just from that point.
You know, and indeed, and obviously the great thing you're doing here is by moving to water. I completely understand the methodology, which is I approve of exactly, which is the idea of using the water to make sure there's no issue about using GPS to get the right height, and you make sure.
I would just kind of bring closure to this. That the fact is. That carpenter's level I was using, the 3-foot carpenter's level, I've checked it numerous times. It's in good condition and works correct, works well. And the fact is that the two spikes were set to within squibs of each other of being.
I thought you'd although I was saying it was a theoretical point that was supposed to be made. But I knew that in practice you would do a good job of it. So I was thinking, hold on.
It's
and I think the great point is, and that's why I'm glad you appreciate it, Rumpus. So the reason I picked this one is we're not introducing anything external, right? We're not introducing the radius of a presupposed globe to this. Do you see what I mean? We're
absolutely.
Saying,
I appreciate the whole. Yes, I mean I would amplify that methodology. I mean, you did say it repeatedly, but I think it needs worth re-emphasizing.
Well, I just don't know if everyone got it. You know what I mean? I don't know if everyone understood. Maybe
I'll have a go. Let me have a go then to sort of be on Jess's side. Okay. So the idea is that you need to, the trouble is, how do you find something of the same height above the thing? Now you could do it with GPS, something very complicated, but that means you're relying on GPS to give you heights. How do you do it? How do you make sure that two things a long way away from another are at the same height? Well, if you say that water's level, then you can just simply say, I know what, I'll put my tripod or my theodolite 6 inches above the water level on 2 pieces of water 500 meters apart. So we're not relying on any GPS. You're not relying on any assumptions about the flatness or the sphericity of the Earth. You're using water to do the job, which flat earthers seem happy with. So if you've got these two things 6 inches 500 meters apart, then you can say, right, from here we'll now be able to determine whether these lines, these angles will cross or point at one another. And if they don't, if they don't point to one another, we're on a sphere. And if they do point to one another, you're on a flat Earth. And nothing else is involved in this. You're simply using water to define what's flat and level. And so obviously, and I presume, I haven't seen the video, I presume that when you did it, you found that your theodolites weren't pointing at one another.
Correct. And the thing is the one we've looked at today was the 7,000 foot one. I did one previous to that of only about an 800 foot lake called Union Lake, and found the exact same thing, only smaller magnitude. But it was a proof of concept. I went there quickly to say, hey, would this test work if I just set 2 points level with each other using the lake as the level reference? What will I see? What will it look like? And on that test, I had GPS running simultaneously. It was a more elaborate test. I had a set of 4 points. So GPS was operating next to me while I was doing my theodolite observations. And that is the test that spurred me to say, hey, go over to Cooper Lake. It's longer. And in that test, I did what was presented here. And again, I want to emphasize, all of my early tests were done with an optical mechanical theodolite, an old-fashioned theodolite used in the days of triangulation without any software, without any program.
Yeah, I think that's the other important point. There's no GPS going on here. There's no
Right.
digital readings, are there? There's no
Right.
lasers. There's no
No
EDM.
lasers, no measure. No
Exactly. It's
measuring.
got two things. It's got a measuring a level, and then it's got a something that you can sight through optically and do a level with crosshairs.
And this is also a very similar to George's thing, because George used the trick of having some ice over there, and he was able to measure things relative to a water level. So, in fact, you've both done a sort of similar test in this regard, using water to get your supposed level, and then measuring things from that.
Hey,
in your case.
I was so impressed with what George was doing. I saw him on the non sequitur show or some hangout, and he had an opportunity to present what he was in the midst of doing. I had to go. I mean, I forget how was that 2 years ago, George? I had to get on a plane and go there and help and do whatever I could do, because that was a great test. It's a great laboratory.
Yeah.
Of course, our new one now is the Great Salt Lake. That piece of water. Now talk about this. This test here, I had 7,000 feet. The Great Salt Lake is what, like, I think you got like 20 to 30 miles of glass-like water.
And you're going to do the same thing as you did here.
Not a ripple. Well, we could do a lot of different things there. There's a lot of testing that could be done there just for the fun of it. I mean, you've got Mind of God's idea of which I think is probably being developed or changing as we've been having these discussions. But there's that. There's the idea of taking one of those little Roboton little boats, 3-foot little boat, put GPS on it and run some profiles. But you can do these optical types of tests as well. So,
I mean, going back to the refraction thing. I mean, I haven't done the maths for your there's 7,000 feet. I don't know how many that meters. Have you worked out what the standard refraction? How many? I mean, that's because the fraction is normally, I think, about 15 to 20%. So, in other words, I'm saying I would predict in this measurement that you did in whenever it was 2016, you're going to get a 15 or 20% error in what you've measured it. So, is that what you're saying? The error
yes, standard refraction would need to be applied to correct those zenith angles, but they are still going to sum to greater than 180 degrees. That's for sure. But I threw these things up there to just see what would happen. Here are some measurements, and I didn't encumber them with anything else. I just said, here's the data, and that's mostly what's on my blog is just a record of the measurements themselves.
So you didn't use that to go and get a radius for the Earth, for instance?
Correct. Did not do that. No.
Oh, okay. I mean, I'd be interested in doing that, actually. I don't know if Toady's already done this.
I haven't. No.
Okay, because that's my immediate reaction would be say, right, what using
is the radius
using the raw data, forget about refraction for the moment.
Correct.
Just take it and then see what radius that comes on. If it comes up with 7/6R, that'll be quite interesting.
Oh, well, at that time when I did this test, I wasn't even thinking about, hey, can I measure radius with this or anything like that. It was simply, what does it look like across this lake? What does it look like from end to end, looking both ways? What does that look like? Just to try to capture a picture or two of that. Did that, and then what happens if I measure the vertical angles? And on a flat Earth, you wouldn't. Maybe this is a question for flat earthers. On a flat Earth model, shouldn't those two plumb lines be parallel with each other? Therefore, because they're set at the same elevation, shouldn't the sum of those vertical angles be 180 degrees? But we never find that, ever, not ever. It's always greater. And it turns out that the amount it's greater than 180, the sum, corresponds to the difference in latitude and longitude between the two.
1 octane, yeah.
Yeah. So whether it's 1,000 feet, 500 feet. Now, my optical theodolite, the T2, is a 1 arcsecond instrument. And if I did this in 100 feet, I would be inside the threshold of my ability to determine the noise in the measurement compared to what you're actually measuring. So that's too short. I can't do 100 feet. I have done 200 feet. Because I felt like, hey, how short of a line can be measured and have this be true? And I've been able to repeat it quite consistently at about 200 feet. But again, that's pretty close. So I say, hey, let's go with 500, go with 1,000. Again, at those distances, and this is where I'm trying to get people to realize that if you look at these shorter distances, refraction doesn't really contribute much. Would you agree with that, Rumpus?
Well, I would say it depends on the day, of course.
Of course,
but,
well, yeah.
But if we go for a passive day, then obviously, it's, as I say, I believe you're going to get 20% error, something like that.
Yeah, but again, in 1,000 feet or 500 feet on a crisp, cool autumn day, good, very good conditions, and do it in the afternoon. This is when the turbulence is going to be least.
And remember, you're doing it off the water in those pictures. If you take a look at it, obviously.
On land, like
on land, all right.
It doesn't have to be water. You could just.
Your pictures didn't look like there was a lot of refraction there. Yeah.
You could take an auto level.
Well, hold on. You wouldn't expect when you say there's a lot of refraction, Toady.
Sorry, I mean mirroring. I mean,
right. That's in mirage, which is something else.
Exactly. Yeah.
Looming.
Of course, you're not going to see refraction. Of course.
Looming is your enemy because looming doesn't scale things. You can't detect it. Unless you're using the simultaneous reciprocal refraction that I think that I don't know if Jesse's done. But so I think you're going to get 20. So when you measured when you decided they weren't crossing, did you have two theodolites looking at one another in the end in your experiment? I think. Did you say?
No, in this case, it's
or just one.
Me observing a target on the other side.
Right. So how much above the horizontal? So how did you measure that? Did you measure that as an angle? Did you actually go around
vertical angles, zenith angles actually?
Right. Okay. So you got an angle basically that wasn't 90 degrees.
Correct.
And so you've got something like what 88 or something degrees or something for.
Can I share the results again, Rumpus?
Yeah. Sorry, I missed that. I was busy drawing my diagram when that happened.
Yeah, it's all right. Yeah. Okay, I'll share the results again. Hang on. How do I share?
Sorry. Yes, I missed. I was busy drawing.
Here we go. I'll share again. Share screen. There we go.
And then obviously if you multiply that by the distance, you should get. All right. Yeah, I didn't see this diagram. Yeah.
Yeah. There's this one, and there's another good one before. Is this one giving you what you want?
Has that got the angle then that was below? It was the zenith angle. Where's that then? Oh, there we are. Is that 0.86? Is that no? Oh, here we go. 90. All right. So 90 degrees.
90 and 33. Yeah. Arc seconds.
Right.
Yeah.
I see. So 33 seconds. Okay. Right. Yeah. Okay. And then, but you didn't then carry on to say what does that 33 seconds equate to over the distance of 7,000 feet?
No.
How much you would expect? In other words, how much? If you put your target, you could then say. I mean, obviously, you could move your target. In other words, how much would you have had to move your target up to see it square in the target of your theodolite? Presuming that was whatever that.
Those are things that can be done. That's for sure. I didn't. Yeah. This is just. It was very simple. Set these target and instrument up at level with each other, and then make these measurements.
Yeah.
That was.
I wouldn't have been able to resist then using that to work out what radius you covered. So yes, okay.
It still can be done. But where I'm going with this now is, like I said, a lot of the emphasis or what I'm concentrating on doing now are shorter tests, where refraction is minimal. I mean, so minimal you could just ignore it. And we're talking about a 500-foot length line where it doesn't have to be over water because you can take an auto level and make the two pins level with each other. And then you can set the instrument up and the target up to be level with each other so that they are at the identical height, and measure the zenith angles. And I've done this in a park near me, and I've done it like repeatedly.
Quick question, Jesse. How does the auto level work? Yeah, how does the auto level actually level? Does it do it on GPS? Does it do it on something else?
They're not. Yeah, the auto level.
Can I add something here? Because I noticed Toady in one of his view graphs had dumpy level in there, and there seems to be confusion because I had a guy in Australia, what he called himself, Fipi. Remember Fipi? He was trying to claim that my measurements were biased because I could put a bias on my auto level, which you cannot do. There's a fundamental difference between dumpy levels and auto levels. Is an auto level has an internal compensator that once it is properly within a few degrees of being level, the compensator takes over and the optics adjust themselves to be tangent to the earth, whereas the dumpy level does not do that. A dumpy level does not have an internal compensator and it has typically 4 adjustment screws on its base, and you tighten one while you untighten the opposite one to get the thing level. It takes a lot more
Yeah,
And
that's the one I've used at a dumpy
adjustment-
level. It takes ages to.
to level,
dumpy
whereas an auto level has 3 adjustment screws. And once you get that base within a degree or 2 of being level, the internal compensator takes over and the optics float and level themselves to a vector going to the center of the earth. There's basically like a plumb blob in there that adjusts itself to the a vector line to the center of the earth, and the optics are tied to that. So there is no way to add a bias to an auto level. You can tilt the base a little bit, and you'll see the crosshairs move up and down, and then they'll finally settle to where they were before you moved the base.
Which is an actual check we do when we're doing high precision leveling. We want to make sure that that compensator is not hung up, So when you level the instrument, you take your reading, because this is not a digital instrument that records the readings. It's one that you do read the rod. Some of them have a little button. You press the button, and you'll see the crosshair jump and then settle down. And what that did is it checked to make sure that the compensator is operational. It's working correctly. If you don't have that little button, you could just tap it with your finger, and you'll hear a little jingle. You'll hear a little tingling sound in there, because that is a mechanical device. That pendulum is floating. And like George said, the crosshair will move and it will settle back down on your reading. So you've just done an instrument check.
Now, you want to make sure your compensator isn't hung up. So
that's right. That's right.
Jesse says you tap it or you move the base a little bit, and you see the crosshairs jump, and they'll settle to exactly the same spot they were before you tapped or moved the base at all.
So how do you level a dumpy thing then if you haven't got this compensator in there?
Now that has
takes a lot of skill.
That's got a long striding level. It has a long level tube, a level vial with a spirit level vial, with graduations, just the same way as a theodolite has.
And then, then you manually have to jiggle it.
You do.
Then you have to manually jiggle it, do you, yourself? And then
there's
all
no
the bubbles
jiggling.
here.
With
There's
the
no
dumpy
jiggling.
level,
You've got 3.
the dumpy level is simply this: is it level or not? If it's not level, you're not going to be getting good readings. So you level up that instrument using the level vial, looking at the graduations, and then you take.
So you have to look at some bubble and say, is it in the middle or not?
That's right.
Keep in mind, with the dumpy level, you can add a bias. You can add a bias to a dumpy level. You cannot.
I see. I hadn't quite worked out what you had to use. So optically, you look at it and say, "Oh, look, is it level?" Not by looking at the bubbles, and then say by jiggling those 3 adjustments until eventually you get the bubble in the right spot, and think, "Oh, thank God, I've done that." But you can
That's
top it up.
why George's suggestion of using an auto level, if we do go out and do some experiments in the UK or something, would be a really good thing to use, because I think dumpy levels, unless you're used to using them a lot, they do take, in my experience, and I don't use them very often, ages to get them level.
Yeah, the pros and cons here. The advantage that you have on a dumpy level versus an auto level is a dumpy level isn't as sensitive to vibrations, whereas the auto level will. If you have wind, buffeting the auto level, or vibrations in the ground,
get on a construction site.
With the dumpy level, you will not.
If you're on a construction site where they're using these vibra rollers, the rollers that have a big vibrating machine in them to compact soil, and you look at that level, it's just jumping everywhere. So obviously you're not going to be doing any leveling when that phase of construction is taking place. Not going to happen.
Earlier, Jesse,
the auto level is vibration sensitive, whereas the dumpy level is not so.
Right.
Earlier, Jesse, you said something like on one day when you were using over a small distance or something, you said you knew there was little refraction. I don't quite understand how you could justify that statement.
In a short line of 500 feet, right? The effective refraction is going to be
agreed. But then so is curvature as well. So unless you've got a super sensitive auto level, the trouble is obviously refraction is a sort of function of the curve. So unfortunately, as the curve gets bigger, so is the refraction. And as you reduce the refraction effect, you're also reducing the curve effect. So you're fighting against this sort of 20-30% depending on what the bloody refraction's up to all the time.
So in this,
you can choose an optimal day though, right?
No, of course. You could
Yeah.
do it.
Yeah,
Under,
but how do you decide, Metal, what an optimal day is? How do you decide that your refraction is? Because there's standard refraction, which is 7/6R, and then you've got to decide, well, okay, is that what I'm being subjected to? Because you can't even be sure.
One of the things you can do, Rumpus, like you use for calibrating the instruments, is you can set your instrument in the center and have your two targets, one to the left, one to the right, to get things set up by doing a back sight and a foresight to the two targets where you're in the center, and you would expect the refraction to basically be about the same looking to the right and to the left to set up your targets.
now, in this case, these short line tests, I'm not using an auto level. I used an auto level only to determine
you could do the same thing with the theodolite, but sitting in the center. Set up two targets.
Let me answer what he was asking about. Is that I used a high precision digital level to determine the differences in elevation between this network of, I think I have like 5 points over there in the shape of like a quadrilateral. So I've got the perimeter and I've got the cross measurements between them.
So what you're basically...
then what I'm doing is I'm taking a theodolite. I'm using my Wild T2 theodolite. I've used an electronic 1 arc second total station instrument. I'm measuring zenith angles, and I'm interested in seeing if I can determine the tilt between the two plumb lines at either end of these lines, and it works quite well.
Right. So what you're saying is because you've got some very high resolution equipment, you can bring it closer, reduce the effect of refraction over shorter distances, and still get a reasonable result.
That's exactly where I'm going with it. Thank you. Yep.
Right.
Yeah.
Okay.
1 arc second is a pretty darn narrow error bar there, so I would assume, yeah, you could get very accurate readings up to 500 feet.
And I was just curious. I thought, hey, I mean, we've done all of these long distance types of surveys, and it raises lots of questions. What could I do to possibly take out of the equation the aspect of refraction or any other atmospheric disturbance, anything? Let's go close. And I wanted to see, well, how close can I go? And like I said, I didn't do 100 feet because I thought that's just inside. Anything there would be not useful because you would be really inside the ability to make a determination. So I've done 200 feet, but I'm real comfortable at 500 feet to 1,000 feet. I'm talking several hundred meters in all directions, north, south, east, west. You see the same thing over and over. And I've presented this, and I've done it over and over, and I've shown it. It's worth looking at. It's worth.
Yeah, I haven't. I've been meaning to watch your sound video. Yeah, I haven't watched all your videos, I'm afraid. Yeah, so I missed this one completely. But yeah,
the other things to look at, Rumpus, is I don't know if you looked at Jess's WordPress, because actually the videos, are great, but actually Jess's got, I don't know if you've seen his blog. It's really very good. It's got a lot of the measurements on it. Yeah, and you'd be probably more interested in that. That's where I got a lot of the stuff from, rather than from the video. Yeah.
Right. Yes, because well, obviously, it's the nice thing is if obviously seeing things over longer distances and saying, you're going to predict, you can measure, a target being off by 4 or 5 meters or something. It's very nice to see visually, but then obviously this refraction beast gets involved, and obviously if you want to correct for that using your reciprocal simultaneous measurement, then obviously you have to assume the value of the Earth to make that correction.
Well, now you're entering into the topic that I'm pursuing right now with Larry Scott, and you may have seen Larry jump into some chats and comments before.
No, I haven't.
Larry's a surveyor. He's a geodetic surveyor.
Oh, yeah.
He's got 10 years on me in this business, and really comes from the days of old school. And I'm learning a lot from him. I consider him a mentor. I'm learning so much from him because he's had the opportunity to do things I've never done. And I've went and visited him last, I guess that was in December, and we did some long range simultaneous reciprocal zenith angles over 6 miles and 11 miles. And we're planning to do a 25-mile from one mountaintop to another. And you know why we're doing this?
Refraction.
It's fun.
Well, certainly I mean, George has had enormous fun with this stuff, and I've been enjoying George's stuff vicariously because we've been discussing things over the last couple of years with all these. I mean, it's only through George's experiments that I suddenly realised all this refraction business was a problem, and both George and I have been absolutely shocked by how the fact you can't trust your own light, even something a few hundred yards away, is actually being loomed up by an inch or something.
Yeah. Oh, for
it's
sure.
That's ridiculous. You think, we can trust our eyes, but we can't.
Yeah. If you, Rumpus, you'll be interested to see a very interesting picture I posted a few weeks ago on a little hangout I did reporting some of the imagery I took at Antelope Island visiting Tim Osmond. And there's a very interesting picture at the end. I just throw it in there and I said, this blew my mind, but I'm waiting for someone to look at it and let's have a discussion about it.
Oh, right. Okay. Well, I'll go ahead and look at
that. Guys, Jesse and Toady, someone in the chat is asking, they want you to explain the difference between a geocompass and a theodolite.
What's a geocompass?
What is a geocompass? I've not even heard of that.
I get people throwing terms at me. I'm going to go ahead and look up geocompass.
Okay, what about tachometer, Jesse? Because I've heard that used as another substitute term for auto level.
No, tachometer. Here, the geocompass.
It's a tachometer, I think so.
Yeah,
tachometer.
That is a whole. I looked up geocompass and I'm seeing compasses. What are these?
I mean, it doesn't even, to me, the names suggest that they're not even similar instruments. I have no idea.
It looks like a handheld compass. So the difference between that and a theodolite is, a whole lot. But
yeah, a theodolite doesn't seek north or anything like that. I mean, it measures horizontal angles, but you have to establish where your reference point is.
Right. You have to point on one target. Let's call it target A, and you can set 0. You can set the circle to read 0 there. And then if you swing the instrument to the right, let's say to a radio tower 20 miles away, and let's just say you get a reading of 30 degrees. You've basically just said that there's an angle of 30 degrees from my initial sight point that maybe I didn't say what it was. Let's say it's another radio tower. You've just measured the angle between one radio tower and another one from where you are situated. That's what the theodolite does. And you can add to that the ability to measure the vertical angle from the top.
This brings up an interesting point, Jesse, is the thing that I don't think many people realize, that on a theodolite, the horizontal measurements are totally arbitrary. It's with respect to what you establish as a reference. You could establish it. You could put 0 at east. You could put south. You could put north. You could set your 0 anywhere along.
Oh, yeah, that's a good point. I didn't explain that earlier, George. You're right.
Whereas the vertical angle is always measured with 0 pointing towards the center of the earth with your.
Right. And then you also have the option to backsight. We use the term backsight. That means your initial sighting could be the sun. And if you use the sun, now you're actually introducing a true relationship where you have an azimuth, a real azimuth. But you're right, George. Most surveying is basically establishing some arbitrary local setting where you are set up on point A, you backsight point B, and let's just say you have to lay out a building. You're going to turn 90 degrees, because you want it to be square. That's the horizontal angle functionality of a theodolite or total station instrument. Yep.
One thing just I was interested in, I was thinking, given that refraction and the curvature of the Earth is certainly within a reasonable distance, several hundred miles, is effectively a function of the square of the distance. If one could align your theodolites with one another, and you did do lots of little steps, say of about 600, 1 kilometer or something, you could, in theory, I haven't thought this through mathematically, but if you did lots of sightings of 1 kilometer and then moved your theodolite, say, to get 20 kilometers, you wouldn't try and measure it in one go. You'd do it in 20 steps of moving your, of making 20 measurements across a short distance. Therefore, the square issue becomes less important, and therefore you would get less refraction there. Because I'm trying to think of ways of eliminating refraction. Obviously, the simultaneous what's it refraction thing, well, unfortunately, relies on the value of R. Whereas this way, if you were to do it in sort of lots of little steps, you would not be relying on that to eliminate refraction as an issue.
Well, you're going to be, I think, interested in the next hangout I do with Larry. I tried to have it last week, but he had some internet issues and it just wasn't working, so I shut it down. So we're going to do it again, and it is all about measuring refraction with simultaneous reciprocal zenith angles over 11 miles and 6 miles. So basically, we're going to present the results of the work we did back in December, and the change in elevation is pretty good too. We're measuring from a mountaintop down to a point near an airport. I forget what I think it's over 1,000 feet in elevation change. I could have that wrong, but it's considerable. Let's put it that way. It's not a small change in elevation. So, but yeah, I'll make sure you know when we're going to do that. So
yeah, I'd be interested to say what you think, or asking your pal whether that you could do it in, say, if you've got a measurement, say 20 kilometers, you could then chop it up into 21 kilometer measurements, and then in that way see how well that would eliminate refraction. Because obviously you can backside, presumably, because the nice thing about obviously a theodolite is you can move 1 kilometer away, then look back.
You'd have to find a place where you could see the long range and those increments. And guess what? I'm visualizing
Salt Lake City. Salt Lake.
I'm just visualizing somewhere along Route 80 in Utah, because you could find a point up on one of those mountains, and you could get close to it. Let's say within 1K, and then do what you're saying. Keep marching 1K, 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 and that would be an really interesting data set right there.
Because this is I mean, I keep on talking about the mind of God and the issue with you in the past, and the idea that to validate GPS, which is what Mind of God really wants to do, although he didn't really, you seem to be confused with him about what he was trying to do.
I didn't know it was anything to do with validating GPS.
Well, that's the point, because he wants to prove, because he obviously doesn't believe what GPS is giving you the right result. So he's a flat earther. He wants to show that GPS is invalid, and you didn't seem to understand that was his objective.
No, I never got that. I never got that as the.
No, I don't think so, Rumpus.
That's what he's trying to do.
No.
Because if he accepts, well, hold on. If he accepts,
I don't think he's doing that.
He is.
You could imply that he is, but
I've spoken to him
that
subsequently.
could be a logical implication.
Right, look.
I don't think he overtly.
Let me make the point.
No.
The guy's not even here, and we're managing to talk about it. Rumpus, I will not forgive you for this.
We know that water, in terms of GPS, has been measured before and surveyed, and so we know that the water level, the GPS gives us a spherical result. We know that's the case.
Rumpus, wait. He's not here, so we can't do this.
Okay, but I'm telling you.
And here's the other thing. Here's the other thing.
Hold on. I would like to finish my sentence, please. Right, we know in GPS land that the world is spherical. We know this. We also know that water follows the spherical thing. We know this. This is established fact. Now, the point is he's got to challenge that, and then the whole point was this straight line. So this is why I'm suggesting a real world straight line, and this idea of doing little 1 kilometer steps, because we can't easily produce in the real world something long and straight, or even measure it to do it optically because of refraction. If you're thinking these 21 kilometer steps I was talking about is at least some way of getting something that's possibly going to be straighter than any of the other means of trying to generate something straight.
It turns out, I heard what you said about GPS, and I've been trying to get people in the last year since doing Lake Pontchartrain to understand GPS is not a curved measuring system.
Yeah, but it measures a curve. Yes, yeah.
No, listen. It is a three-dimensional.
Yeah. Jesse, I understand this. It's a three-dimensional Cartesian orthogonal system, but it shows the water surface in three curves, isn't it?
Man. I'm going to call Jose in on you. No, just listen. People have to recognize what's happening with GPS, and I don't. Aside from the fact of whether it's satellites or not, I've gone through the point of showing it being used in construction, agriculture, and all types of various applications. And I don't care. If you want to believe it comes from cell towers or whatever, let's just set that aside for a minute. The fact is, it measures wonderfully. It
Yeah,
measures
if
very
you
well.
understand my
And
point,
so,
Jesse. I
yeah, but
accept perfectly it's a three-dimensional orthogonal Cartesian system, but it shows the
that's
Earth to be a
important.
sphere, and it
Well,
shows water to be a sphere as well.
well, it sure does,
Right,
but
exactly.
you know,
So that's why it's got to invalidate it.
but let the test proceed and
Indeed,
let it be
but-
shown. You know,
right,
that's
but
it.
just pointing out
But it isn't about whether or not he's
It is.
claiming to
You
validate
understand-
GPS.
Rumpus, you understand this. I understand this. Toady understands this. Jesse understands this. Mind of God does not.
Well, no, Jesse
Let
didn't
him
seem to
run
understand
his
this.
tests.
Jesse didn't seem to understand this. And Mind of God picked it up a week ago. We had a sort of hangout, and he finally understood what he was. You know, he actually articulated it. That although he hadn't articulated it earlier to you, I don't think. What he's trying to do is to get something straight in the real world and see if GPS says that's straight in the real world. And if it is straight in the real world and straight in GPS, he's going to hold on. That means that GPS is validated. If he finds his straight thing does not have straight coordinates in the GPS world, then he can say, GPS is naughty, and all these spherical shapes that GPS returns to us for the water are invalid, and therefore the Earth's not a sphere.
All right, now he's not here. That's your summary of what you think he's saying, and I haven't heard him say that. Now I'm not going to.
No, because he hasn't articulated it properly.
Okay, well, but the fact remains.
Yeah, we need to hear from him.
even if that is part of what he's out to do, the test will, let's let that roll. Let it. I keep saying this about everything. The measurements speak for themselves. Just look at the data. If you don't like it, repeat it. And if you don't like it, you've got to say why. You've got to.
But the point is,
are we off the air here?
Right, but the point is, if in GPS land you're getting these measurements, they're not being independently verified by some physical external means of measuring it, i.e., using a.
Well, let's take your test, Rumpus. The idea of doing the 20K
variation
over 1K increments. We would do theodolite-based measurements. We would put a target up on a mountain. And then go 1K away, zenith angle measurements to it, also GPS, go another kilometer.
Exactly.
Boom, boom, boom. And you would have both. And
exactly,
what you'll find out, what you'll find out is that the GPS is dx, dy, dz vectors.
That's my cue.
Absolute straight line vectors.
That's my cue to jump in. I heard boom. I am amazed that the link is being up for about 40 minutes. I've been spamming it like crazy on the chat. No flat earthers came in. Thank you, Earth is seriously flat. You came in the beginning when I posted the link. You made a question. You behaved well. Thank you very much. But I mean, it's a great opportunity for anybody to come. I'm gonna let it roll for another 15 minutes or so, and then shut it down. So carry on, guys.
Was that me that said boom? I tend to do that.
Yeah, right. Yeah.
Right.
It's just
right. So you're finally picking up what I'm saying here. So my idea, obviously, the way to validate GPS to therefore show that when GPS measurements you're going to do surveying of this water come back with a curve shape, then we've got to say, is GPS valid? And then the only way to do that is to find something in the real world that you've measured out to be a straight line, i.e. like this 20 kilometer, although it's still going to be subject to refraction, but it will be a one way at least of reducing the effect. Because obviously the problem then is how do you decide to correct for refraction? Although, as we agreed earlier, it's normally
I should mention the reciprocal zenith angle tests that Larry Scott and I did. The 11 mile, 6 mile, and we have a shorter one too.
Right,
those are all GPS,
doesn't it, Jesse? The problem with that test relies on you assuming the radius of the Earth.
Well, but I was just adding to it that we did GPS those points as well.
But the point is that the flat Earth is going to say GPS is being twisted to make the Earth look spherical when it isn't, and they're then going to say. What's the other thing so if you're not assuming the radius of the Earth and the simultaneous reciprocal calculation is also something you're introducing that you can't validate, whereas your test with along the lake you didn't involve any of those things, which is what made it so good.
So that's why I picked it. But can I just come in, because I did put this presentation together, part one, for Mind of God. I know he's not here, so I think it is important, that if you didn't trust GPS, that you would want to validate it against a straight line. And the reason that I put the whole of this presentation together was to show that you can create, using W levels, theodolites, or auto levels, an actual physical straight line. And Jesse did it, and he put, those points in the ground. Of course, it then shows that obviously there's a curve. But the point is that you can, with the equipment, very basic equipment, at least establish something that you do know in reality is straight.
And I did GPS those. But
you did, and that's
GPS,
why we rushed through that bit at the end, didn't we?
Right, and that's a sideline. Just and by the way, the GPS confirmed the same thing.
Confirmed the same
but
thing,
it wasn't
exactly.
part of the initial. And I'm glad you took the time to add a lot of the detail I sometimes am impatient to provide.
Yeah, because I think it's an important point that test did also validate the GPS, right? Which is my thing. GPS is my thing, right? So you know, but you know, that's why I wanted to.
There must have been some refraction error in there, at least. Well, I say, but it's 20%. So I'm just saying, okay, so you could argue, well, okay, if we're 20% out on the result this would give for the radius of the Earth, okay, that's fine. That's what we expect with refraction. But just would have been nice if we could have a system to try and, if we can do it with, as I say, this little stepping along 1 kilometer, you can at least try and get something that's going to be a bit closer to a straight line than you would otherwise do if you tried to, and you wouldn't have to use the
Is there not a way, Jesse, that you could do backsighting and foresighting that's been mentioned a couple of times? And when I read up about it, could you not start to level out some of the errors, or then would you adjust your measurements if you did backsighting and foresighting? Do you see what I mean? Because obviously the bit in the middle, you can start to remove some of the errors.
What do you mean when you're talking about backsighting?
So rather than just sighting in a chain, right? Like, I don't know, 1 kilometer, 1 kilometer, 1 kilometer, 1 kilometer. You know, any error that you get, you might start to build on that error, right? Yeah, because of each sighting, let's say, in whichever direction you're going in. Is it not possible to have a target in 2 directions? Yep. And then take an azimuth measure to that, so you're starting to correct even as you're doing each, I don't know, half a kilometer, whatever you're doing.
Right. Yeah. So, you know, let's say point A is near where you have this point up on this mountain, right? So you're at point A, and you're going to aim up at the mountain. Behind you would be point B. You could literally sight point B, turn up to the mountain, get that set of measurements, then move to B, right? And C would be behind you now, another K. So you would always link them together. You'd backsight 1K away.
Right. So I misunderstood the method. Okay.
Yeah.
Right,
and then
perfect.
maybe and then turn to the first point you were at. So you would have, you know, C, B, and A, and then also up to the mountain. So at each K away that you go, you're tying those together. Okay. So you're going to have reciprocal measurements there, and you keep shooting up to the mountain. And for all I know, we could actually have an observer up there
as well,
measuring to you. So you're going to have continuous zenith angle measurements each step of the way. What a great data set.
That would be fantastic.
Who's up for it? Let's do it.
So the problem for me, Jesse, is, right, I don't do these things on a day-to-day, and I'm a very visual person, which is why I drew all those diagrams, right, to try to explain it also to myself and to others. Because a bit like Rumpus with his diagrams, I'm having trouble visualizing points A, B, and C, though I can see it now, right? I got exactly what you mean. And as you say, if you've got some up the mountain as well, you could sight back, right, from up the mountain to the points, because you could have a target, couldn't you, where you were? Yeah. So yeah, I could see how that would work. Yeah.
And, you know, we're talking all about measuring, right? And measuring of all types, whether it's GPS, putting GPS on a little boat, doing, you know, what we just described, zenith angles, each K. The thing about all of this is that we can do this, and it really does just build upon what has been done for hundreds of years, although we're using electronic distance measuring now, and we have a lot of, you know, electronic total station instruments, but none of that changes what was done by the Romans with strings and plumb bobs and little water level, you know, little channels with water in it that you could sight across. Those principles are still there. I look in the chat, and there's so much mockery, right, going on, and it's like,
best not to look. That's all I do.
Yeah, but I'm just smiling, thinking, okay, now
you shields, you're not measuring it properly. You're
but the thing is, like, what do they propose? Okay, now if you want to have a belief in a flat Earth, that's okay. Now, do you? That would mean then you cannot trust in any of the maps that we have, and you. I guess you're lost. Like, how are you going to get to your grandmom's house 2 states away? So, you know, isn't there a need to then remeasure the Earth? And then, well, how are you going to do it? If you don't like total station instruments because they're flawed or whatever the claim is,
Presumably, they think there's a load of flat Earth surveyors running around actually doing the real work to make sure everything doesn't fall down and joins up correctly.
I've never heard that one. I never heard that one.
I've never heard that
are
one.
the real ones, and you're just the cover story.
Well, no, there must be, right? Because all of the globe Earth surveyors, that was part of my thesis earlier on, right? They're making all these adjustments, right? They're putting all these plaques, right? USGS plaques all around the place, triangulation points. Go on.
I have a question about the total station, though. You said that it uses an infrared beam, right? So it's in the infrared band of frequencies, right?
Some of them are. The EDM equipment, the EDM
only for
instruments,
ranging, though.
There are different types. But
I mein, it goes into the gigahertz range of frequencies, then, right? So
no. It's just a little bit below the visible range. You're in the terahertz range.
Right.
The old
I was
HP.
just wondering about that.
Yeah.
Yeah.
Well, the old HP had a visible beam. You could actually see that red beam come out.
When I went to when I joined HP Labs, the civil engineering division was just over the wall from my cubicle, and they had just introduced the Bear at that time. They called it the Bear. And,
was that? Yeah.
That was the first theodolite to have a laser ranging system.
I have a question about this Mind of God experiment with the drone. How is he proposing to make sure that the drone does fly in a perfectly straight path?
He's abandoned that.
Yeah, we're on water now.
Yeah.
We had a good conversation about using the Great Salt Lake as the thing to model that surface of that water.
Okay. All right.
Yeah, Louis, we got him to finally abandon the airborne drone idea.
Well, that's good.
It came down to just having a conversation about what's practically can be done. There's one thing to think, do a thought experiment. Hey, if we could do this and this and this, but then it became necessary to really get down to, well, what physically can we do? And I tried to bring to it the actual surveying that we do now to do anything you see around you, whether it's a bridge, tunnel, or whatnot. There is the design of the thing that doesn't exist yet. That's the proposed thing, a designed bridge or what have you. And in the case of what he had in mind, it was a series of blue dots, these theoretical arranged points.
Which didn't make any sense at all.
Well, look, I get what it's going to show.
This is what worried me a little bit. In fact, you thought you understood what he was doing because he didn't really understand what he was doing. I didn't understand what you thought he was, because you seemed to think he was offering some sort of valid idea, and he wasn't. Well, so I'm very confused.
The ideas are developing. Rumpus, the ideas are developing, right? That's the idea of people discussing
they were obviously
things.
Wrong.
All right.
Okay.
People discussing
Schrodinger.
Things, yeah?
Well,
Schrodinger's something. I'm not sure what his name is. He's been trying to say something.
Okay.
Schrodinger, you there? Okay.
Well,
all right.
Well, anyway,
I'm gonna tell you something, George. Listen, George.
Sorry, I was muted.
Oh, sorry. Go ahead.
Yeah, when I first popped in, you guys were talking about that there was no flat earthers here, and I just wanted to mention it's getting harder and harder to get any of them to come out of the woodwork. Last night, the flat earther on non sequitur just didn't show. And that's happening more and more. But, we spend weeks setting up these debates. Gets to the last minute and crickets.
Yeah.
Well, they're on the
Metal was saying something, was addressing me or something. What did you have?
Oh yeah. Well, what I was about to say was that the things that Mind of God has conceded in the presence of us on Jose's channel, such as that video that he has of him walking across the floor. He says that he conceded to us that it's not valid, right? And the whole thing where he wants to fly a drone in a perfectly straight line, which he conceded to us isn't a good valid idea. He will go into other venues and just readily pop them off. Like,
yeah.
Hey, I just did a video of me walking across the a floor, and it shows that it's flat.
I've seen that happen with other flat earthers too. And they're amongst us. They say one thing and then they go into their comfortable space and they go.
But that's okay. That's just people being people, right? You know, we're making some progress. Josie's Hangout is good. You know, people are debating stuff. We are adding some level of precision and certainty.
Well,
right?
part of the
audience.
So I don't, you know, at this point, it's fairly obvious. I know Mind of God isn't here to actually talk to me about this, but it's fairly obvious that he's not honest in his intentions with discussing this with us.
I don't think that can necessarily be said, because he can still be honest if the ideas that if he cannot reconcile them to be false, then he's just going to go around saying the ideas because they're the best things that he has. And he's going to say them to as many people as he can. And in that way, he will be testing the integrity of the massive amount of people that he talks to.
And you can still be wrong and confused, can't you? Right?
Yeah, definitely.
Yeah, you can be wrong and confused, right? So you know, I think it's fine. That's why I put all this stuff together to give a good baseline that we can all refer to, or at least help all of our knowledge, right, about dumpy levels and theodolites. I've learned so much today that I didn't know from listening to George and Jessie, and you know, and I researched this, right? So I think, you know, and then we can cut out some of the stuff that is just rubbish, right? You can't do a straight line, you can't do this, you can't do the other, because a lot of it is just hyperbole when I hear it on the chat. And I wanted to try to bring the view from the real world in. All the people who go, thousands of people go to their jobs, you know, tomorrow morning. Do you see what I mean? We'll be using a lot of these techniques and a lot of these things to do real things in the real world, right?
Guys, I need to round it up. I need to go get ready to go to work. Everybody gonna have an opportunity to give me your final thoughts. We're gonna begin with George. George, go ahead. Final thoughts.
No, I'm saying thanks, Jose. I called you Jessie. Sorry, but yeah, thanks. This was a very nice hangout.
Yeah, thank you very much. It started raining like crazy. So, all right, Jesss Koslowski.
I want to say thank you to you, Jose, for running a channel like you do. This is a place that I've felt finally comfortable enough to come into, and it's due to how you run it. And thanks, George, for kind of pinging me here and there when things pop up that are that you think of are interest to me. Toady, awesome job filling in a lot of the details for people to, like you said, see what surveying is. And that's what I'm going to leave it with this, that we can measure. So, you know, you guys who want to just make fun of that, you know, you're just ignoring the fact that you live in a world where surveyors have done everything that you see around you, your sewer system, your water system, the electric transmission system, the highway system, the nautical charts that you can use when you go fishing. It's all surveying. Everywhere you look, it's been done by surveyors over decades and hundreds of years. So, you know, hats off to all of those people before us that we enjoy the fruits of their labor. So anyway, thanks a lot. And I do have to get going, so I'll listen to everyone else. And thanks, and nice talking to all you guys on this panel too.
Thank you very much. I really appreciate it, and always welcome. All right. Thank you.
Awesome.
All right, Louis Hackett.
I had a conversation with Mind of God on Sean G's channel, which did get stricken, so it can no longer live stream. He has a backup channel though, which he has a video on his main channel linking to, so you can see him go live there when he does go live. But in that conversation with Mind of God, I proposed to him a test exactly like the one that was being talked about here earlier with the two platforms with auto levels not looking directly, with the divergence in their line of sight relative to each other. And he said that was an excellent test and he really liked it. So I think he is moving towards the right direction, and I think there's progress that can be made. So there we go. That's my final thoughts.
Cool. Thank you very much, Luis. I appreciate it. Metal Slugs.
Hey, thank you for having me on. Thank you for running a very, very good Hangout platform. And I really enjoyed these presentations. It's great to have experts on this panel doing some great presentations like this. And it's encouraged me to learn a little bit more about theodolites now. So thank you very much, guys.
Thank you for being part of it. Schrodinger scale.
Again, thanks for your hospitality, Jose. I really enjoy when I get a chance to be on here. Everybody check out my video. I released it last night. It's about a crazy lady that likes to go on college campuses and scream at college students about flat Earth. I'm closing in on 400 subs, so I could appreciate all the patronage that my channel gets. So if you want to help me out, go over there and take a look. Thanks.
Cool, thank you very much. You can copy the link on your channel and spam it on my chat a few times so people can click on it and subscribe. Thank you, brother. Yep. Dean, go ahead.
Yeah, I just want to thank George, Jesse, and Toady again for an awesome presentation and the clarity and breaking things down simply. I just thought it was fantastic. Jesse, at the end of this, can I just have like 1 minute of your time after the show rounds up? And yeah, Jose, good show. Hope to be here again.
Yes, I can hang around.
Yeah, the hangout will be running offline once I close it down in a minute. The Rumpus.
Yes, I'm glad to see that we're I still don't think people are realizing what Mind of God was trying to do, and I'm glad to see that people now appreciating that the way to do the test of any value is to have some sort of straight line in the real world, which, as I was suggesting, you could do with this 20 steps of 1 kilometer, which would help reduce the effects of refraction, although I am happy to accept on a sort of passive day is only going to give you a 20% error. But we need to focus on eliminating it as much as possible, and that means you could still do a long distance test in which you would still get big numbers, but hopefully with doing 20 steps, it'd be great if Jesse could do that. And yes, I think Jesse's, I haven't seen that thing of Jesse's using the water, which is very similar to the thing that George did with the having a distance of 5 or whatever it was meters, and then having something measuring relative to some water. I thought was an excellent way of demonstrating that the Earth is a sphere, because of course Jesse got results where the angles were not at 90 degrees, and even if you allow for refraction there, it's still going to show you that the Earth is a sphere. And the fact is you just use nothing more than the fact that water is level and the fact that things are horizontal as a result of plumb lines should hopefully be a good piece of evidence that flat earthers shouldn't really find any way. Well, they are going to find it difficult, except I suppose, but they're going to have very great difficulty providing a logical argument against it. Anyway, thanks.
Thank you very much, Rumpus. Always welcome. And Toady Liley.
Hopefully we'll learn something today. That's why I put it together. Hopefully other people will watch it and we'll come back and discuss some of the things in it. Hopefully it's put us all on the same sort of platform. I hope people enjoyed some of the context of some of the things that I've seen, and I'm very happy to talk about CERN later on, and I'll go away and research a bit of that. I learned a lot today about sort of surveying and plumb bobs more than I already knew. And I think it probably also proves that other people can do diagrams other than just Rumpus, but I think Rumpus's are probably better than mine because they're done in a better package, and I just did them in Photoshop or a PowerPoint or something.
They weren't too bad. They weren't too bad.
Yeah. And that's why I put the joke in at the end. So hopefully everyone enjoyed it, and I think it was a very civil panel. Shame we didn't have maybe more opposition on it, but there's probably a reason for that as well. And thanks, Jose and Jesse and George for doing this at the short notice. Sorry about the timings, and thanks for the hangout, Jose.
Thank you very much, Toady. It was an amazing presentation. I really appreciate it. Everybody should rewatch this hangout because a lot of people was caught up in the chat and they were not paying too much attention. So I encourage you all to revisit this, pay attention to what was presented, and then we'll come back to it. I know tomorrow, in the next few days, some people is going to come back and say like, hey, you know what, I heard this hangout and this was mentioned. Hopefully it happens. So guys, come back to it, see it. Thank you very much, George, for being here also. Thank you very much, Jesss Koslowski, for taking time to do this. Thank you all you guys that joined afterwards. And I'm going to get out of here. Thank you very much. I'll be back tomorrow with the regular open discussion, flat earth and more. I'm out. Boom. Hi.
Boom.
Cheers, guys.
All right. And it is all over. Thank you very much, everybody. Thank you for the super chats, for the support. I really, really appreciate it. Let me show my ugly mugging here in this. So yeah, I had to come inside the house because holy shit, hold on, what's going on here? I messed it up. Yeah, I had to come inside the house because it was pouring outside, raining like a mother, and I got all these little creatures around me just telling me it's raining, I'm afraid. I got two more, one more over there and one more hiding in the kitchen. So yeah, I enjoyed it very much. Thank you, and I'll see you later. Boom. Shh, quiet, there should be impost. Boom. Thank you.